spaces alongside Deansgate Lock. And then finally, we activated the frontage and the sort of the public realm, the street front, by creating a colonnade to Whitworth Street. What that did is it tied the building into the scale of the viaduct behind and the existing Deansgate station, but it also allowed us to step the building out slightly over the existing pavement in order to maximize footprint on what was a very tight site. So in terms of the facade design, there were a number of drivers to the facade design, both aesthetic and technical. These are by no means exhaustive lists. They're just a few of the sort of the key things we want to talk about today. So I'll focus initially on the aesthetics and then hand over to Elena for the sort of more technical. So one of the key drivers was trying to create a facade that responded to the context surrounding areas and the heritage of this part of Manchester and the history of Whitworth Street. We also wanted something that responded to the streetscape, both in terms of connecting to the buildings either side, but how the tower landed on the ground. And this was something that Manchester City Council were incredibly passionate about when we spoke to them during the pre-app, of how that tower reached the ground and yet created something that was of more public and human scale at that base. We wanted to create as well a facade that responded to the building organization and how the internal organization was reflected on the facade. And then we wanted to create something, and this was one thing the client was passionate about, was to create something that was a unique appearance and that would stand out in the growing skyline of Manchester City centre, and then something as well that was reflected, or embodied all of that within the materiality. So the facade design was quite simple. We started off first off looking at the programme of the building. So this created us 4 sort of horizontal stacks in the building, with the amenity at the ground floor where the colonnade was, and then 3 blocks of residential apartment types up the building, dividing it into these 3 bands. We then wanted to try and connect the tower to the base. So by emphasizing the verticality of the structure, that tied the colonnade where it hit the ground through up into the tower, and then that was emphasized further by introducing a sort of secondary solid element running vertically. And then we overlaid that with the articulation of the facade, each band responding differently to the interior layout of the apartment. So what that did for the tower was it created a series of a sort of a framework of these solid terracotta elements across the 3 tower residential facade types. And this then, we were able to infill these with solid, glazed, and ventilation panels. But the 2 most striking elements of the building are obviously the terracotta material and the colonnade to the ground floor. And for both of those, we looked at the history and the heritage of Manchester. Whitworth Street runs east-west across the city, south of the city. To the west is Castlefield. Now, this is obviously an area where the canals meet the railways. It's very industrial. It's got all of the arches and this kind of language of the sort of the viaducts and the bridges, and that helped to inform the arches. Whereas at the other end of Whitworth Street is the Whitworth Conservation Area, where there is a high concentration of terracotta and faience buildings, and that influenced the choice of materiality. So we ended up then with various at the primary elevations, and they are 2 different types of facade. So we have a unitised curtain wall to the tower and a stick system to the base. In order to try and tie those together, one of the key elements was the terracotta and the use of terracotta. So we were quite sort of definite that we wanted to use a single source to ensure that the terracotta was the same across both elements. But we also developed a system where we had 5 general extrusion types, and they were used across the whole building, whether it was cladding the unitized facades at the tower or the columns at the base. And then quickly running through how that then works through the building. At the colonnade level, we have the rain screen clad columns in a range of different profiles, some of which, in order to create the arch, are hand slumped. And then running up the building, we have the different types of facade. So with the terracotta sort of creating the grid, and then infilled with the glazed, the opaque spandrel, and the ventilation panels. And as it goes up the building, it opens up to the top floor to give more glazing to act as a crown at the top of the building. I will hand over.
Right, so Paul has just introduced you the project through the architectural lens, guiding you through the decision that shaped the facade rhythm and how the terracotta gave the tower its character and identity. What I would like to do now is bring you behind the scene and see how those architectural ambitions were translated into an engineered facade system for an high-rise building. Before do that, let me quickly set up the content of this second part of the presentation. As Paul just described, this is not a single facade system. Across the building, we have developed different facade typologies, but today I would like to focus on the residential level, where the unitized facade is used. Not just because it covers most of the envelopes in terms of surface area, but because in a way it is where all of the key constraints and challenges we have faced during the design development came together. From building a 44-story height in a very constrained site to having to deal with very demanding acoustic and thermal performances given by the residential use of the tower. So before going into the technicalities of those constraints, I think it's important to quickly explain how the design of the facade was taken through the Gateway 2 process. Since this is an high-risk building, BSA compliance and delivery consideration were always part of the design since the beginning, and therefore they influenced it quite deeply. During stage 2 and stage 3, we have developed the full design intent, identifying the key constraint, coordinating the performance requirements, and defining how those constraints would have resolved within the facade system. When the project moved into the stage 4, Foki joined the design team with the role of validating our design and further developing it into a deliverable system under the BSA framework. Right, in this context, now that I have set up the context, let's start to see which were the constraints I mentioned earlier, and let's start from the one that was evident since day one, the site and its location. So as you can see, the building sits next to an active railway platform on one side and is surrounded by public roads on all of the other side. And therefore, in this context, even the basic construction operation can become very complex. Think about accessibility, logistics, safe management. And therefore, because of that, the first question we pose ourselves when system to propose was not really what performs well, but actually what can actually be built here safely and efficiently. And this is when the unitized system became the answer, allowing the facade to be prefabricated, including the terracotta overcladding, to be prefabricated off-site and reducing, therefore, the inside complexity. At that point, when the facade system was chosen, we therefore start looking at maximum dimension, geometry of the panels, and this is where the installation strategy became a key driver for those decisions. Yes, because relying only on the tower crane in order to lift and install all of those panels would have created a massive pressure on program and logistics. And therefore, since the beginning, we start looking at alternatives. And those alternatives were including lifting systems such as hoists for the central part, monorail for the core, the area that is looking to the railway, and potentially loading platform with the help, with the use of the tower crane for the wings of the building. These alternatives were not just responding to the facade, but in a way they shape it, they influence it, because at that point, knowing that this would have been the way to install those panels, we were able to set the real limits in terms of maximum dimension of the panel, geometry, weight, for lifting them and handling them. Right, so design system was set, installation strategy was defined, and what we did after was just start designing in detail the facade. And this is when the acoustic became the next major challenge. Yes, because the building is not exposed to one source of noise, it's actually surrounded by them. Well, we are on one side the railway, and therefore we have train noise, braking noise, vibration. On the other side, on all of the other side, we have the public roads, and therefore traffic noise, dense urban activity, and probably the most challenging one across all of them, the nightclub, which is just 10 meters far from the building. And why I say this is the most challenging? Because this relates to low frequencies noise. In fact, the challenge at that point, the question we posed ourselves was not really how loud is it, but more about which type of noise is coming from the nightclub and how it behaves against our facade. And this is where things became much more challenging, in fact. Right, so as I said, Rebellion nightclub, but also the railway, of course, were setting the critical frequencies down in the spectrum at 63 and 125 hertz, where the bus energy sits. And this is very important because curtain walling are not really effective against in dealing with those frequencies. And therefore, we start looking at the system as a complete system, not just at individual assemblies or build-up, including instead framing and interfaces, because at these low frequencies, even a little weak point can become the path through which the sound gets into the building. And how we deal with that? We first tailor the facade according to its acoustic exposure. And therefore, as a result, the lower level, up to level 15, became the high-performance facade zone, where the performance were much tighter, and therefore the facade has to perform much better. So we start looking at build-ups at the beginning of the design, and we try to increase mass where possible on the opaque portion, and we introduce, of course, acoustic interlayer in the glazing. But those measures were not enough. As I said, usually at the low frequencies, acoustic performance are won or lost at the interfaces. And this is where in stage 4, when Foki joined the team, the focus moved from assemblies to framing a specific interfaces, because we want to have the confidence that our design was actually fully achieving the acoustic requirements. And therefore, how we did that? We decided to make up an overall acoustic model of our facade, which is including all of the different panel typologies and interfaces. And from this model, we extracted their performances at each frequencies, which were based on acoustic tests previously run on other projects, which were reflecting almost the same type of interfaces, build-up and framing. And this was create a robust baseline to assess our current design. By the same time, make us confident that when we will have to carry out our project-specific acoustic testing, this performance will be just validated and confirmed. Well, if acoustic was maybe the more evident challenge we were dealing with, thermal performance was actually shaping the facade just as much, but behind the scene. In fact, since the beginning of the design, from stage 2, we work very closely with the future self, which is the MEP team on the job, trying to understand how the facade would have contribute to the building operational energy target. But those targets were actually much more ambitious than the standard part held. In fact, they were part of a wider Be Lean, Be Green strategy. And therefore, as you can see from this table, the target we were have to work with was actually 0.83 against a more relaxed target from the building reg. So based on that, also the thermal performances became a challenge that in a way shape and influence a lot the facade in terms of proportion between opaque and transparent, but also in terms of specific detailing. Sorry. Right. So as for the acoustic, in order to achieve the targets. The strategies couldn't be just introducing high-performance glazing. The facade and the unit themselves has to be studied as a complete system. So how we did that? As Paul shown earlier, we developed since the beginning different facade typology. And then the process of testing them developed along two different paths. On one side, we start looking at glazing ratio, proportion of the panel, and test different configuration in order to see how those configurations would have contribute to the thermal performance. On the other side, we focus on specific detail and try to test how different alternatives could have helped the thermal performance overall while maintaining the architectural intent. So this process led us to a series of options, of course, and configurations. Some of them didn't really work, as you can see from here, a lot of no. But each of them helped us to understand where the performance threshold was and kind of led us towards the optimized solution. So we start refining the detail alongside with the proportion between glazing and opaque. And finally, when this refinement process was completed, we carry out one last very detailed thermal analysis covering all of the different interfaces in our facade. The results of this analysis were then applied across the whole envelopes in order to prove that actually the whole envelopes was achieving the 0.83 target and not just a representative bay. Right, so facade strategy was established, thermal was resolved at the end of stage 3. So when Foki joined the team in stage 4, they obviously developed their own detail using their proprietary system. And keeping the architectural intent as it was, including the panel proportion, as well as the target, of course. And after that, what they did was running their own thermal analysis, of course, and validating and confirm our design. Right, and this brings me to the main point of my presentation. This facade didn't come from a single solution. Instead, it came from a control process of testing, resolution, and refinement. Right, let me conclude with a few considerations from my side, personal. So looking back, what I found most interesting about this project is that none of the key decisions were driven by one discipline. Site influenced installation. Installation influenced the facade system. The facade system has to respond to acoustic, and at the same time, thermal was running in parallel throughout, refining all of them. And this is a reminder that facades are rarely just about appearance or performance or delivery. They are all where all of those ambitions meet. And I think in this, the success of the facade is actually come from the fact that those constraints were embraced rather than fighting. In a way, they were not obstacles to overcome. They became the framework that shaped the facade and gave what gave the tower its strength and character. Thank you.
Thank you, Paul, Elena. I think that's a really interesting example of how constraints and really quite tricky site conditions and heritage intent, architectural intent can really be driven through a project. I think the idea that these constraints aren't things that we're fighting against, but they're actually driving through good design, and tailored solutions to sites is really important. And it's been great to see the scheme. Look forward to seeing it come forward on the skyline the next couple of years. It was also interesting to see how it corresponds to Rob's presentation about 40% glazing among other factors. So I think that's really quite an interesting way of looking at these things. Next up, we've got Iain Wilson from Benx, one of our associate partners today, who's going to be talking about their systems and facade design performance. Welcome, Iain.
Good morning, everybody. In the next session, I'm going to hopefully remind everyone of the importance of designing not just for safety and performance, but for how we actually experience facades as people. Before I do that, a few words on Benx. We supply and develop certified facade systems, rain screen and EWI, as well as all of the components that go with those. We're a mid-size UK company. We have about 100 employees, and we have a strong emphasis on testing and certification. And innovation is at the core of everything we do. Now, we've been in this business for almost 3 decades now, and it's absolutely crystal clear to us that a facade does so much more than merely enclose a building. Since my background's in finance, I'm going to start with a few numbers. Our brains register the exterior of a building, the built environment, in about 50 milliseconds. That's long before conscious thought kicks in. In surveys, about 3/4 of people acknowledge that this exterior built environment affects their mood, can even impact their mental health. And eye tracking technology tells us that it's the interaction zone of 0 to 3 meters from street level that has the greatest impact. And finally, the engagement ratio of 100:1 means that the number of people experiencing a building from the outside to those who actually use it can easily be 100:1, sometimes more than 1,000:1. So facades definitely matter. Now, when we come to design a facade, as I'm sure you all know, we're effectively seeking a point in a 3-dimensional space involving color, texture, and form. And broadly speaking, color elicits emotional responses, texture helps define scale and permanence, and form creates depth and stimulates curiosity. And each has an important role to play in how a building affects us as people. Now, I'm going to focus largely on color due to time constraints, but I will touch on the other 2 dimensions. I think our relationship with color is neatly summed up by French artist Paul Cézanne, considered by many to be the father of modern art. There is substantial evidence that color has neurological, physiological, and emotional effects on us. It can actually impact our blood pressure, our heart rate, our body temperature, and hormone production. And we can review our response to color as a spectrum, where at one end, warmer hues prompt energy and urgency, while cooler shades signify calm, trust, and safety. In facade design, warm colors such as reds, oranges, and terracottas are often used in retail, hospitality, and entertainment. These colors, again, have been shown to increase heart rate and cortisol production within seconds. And they can make spaces feel physically warmer and give the impression of depth. However, as many things in life, balance is key. And at high saturation and scale, these colors can potentially become overwhelming. Cool and neutral tones convey calm and focus with a sense of authority and competence. They can help concentration and reduce stress, which is why they're often used in civic or corporate and sometimes healthcare settings. But again, balance is important, and here texture can be key to ensuring that they don't feel too cold. Natural colors are often considered to be restorative and calming. Typical response to green hues is relaxed wakefulness, making them ideal for education, healthcare, and sometimes urban workspaces. Earth tones suggest security, warmth, and stability, and are often used in high-rise. But on overcast days, certain hues can appear a bit drab. Unfortunately, we never have those in the UK. Just a minute on the second dimension, texture. And we know from psychology that natural textures tend to elicit positive emotional responses. Plant-covered facades, as well as wood grain, natural stone, and brickwork have been shown to reduce stress levels. In contrast, highly artificial, smooth, featureless finishes can create a sense of discomfort or sterility. And form, the third dimension, also has distinct responses. Symmetry, grids, repetition, and flowing forms can feel stable and calm, harmonious, but at scale, if overdone, can be a bit monotonous. On the other hand, irregular, fragmented, chaotic forms can feel dynamic and interesting, but again, unsettling if too unstructured. So balance is key. And to emphasize that point, there is a sweet spot where these three dimensions we engage with them most effectively. That's what I like to think of as the Goldilocks zone. If it's too simple, the facade can be boring or forgettable, whereas too complex can be overwhelming or cognitively taxing. So we're looking for that balanced complexity where the facade is engaging but understandable. I'm just going to share a few examples to illustrate the use of these three elements in facades. This is a row of riverfront buildings in Innsbruck, Austria. And I don't know about you, but my eye is immediately drawn to the stunning backdrop behind these rather mundane facades. I have to apologize, I tricked you. This is the actual image. And I only did that to emphasize the impact of color. It brings so much foreground interest and depth to this picture now, while complementing that backdrop. Some of you will recognize Gaudi's Casa Mila in Barcelona, a residential building completed in 1912. This iconic facade balances the uniformity of repetition with interesting deviations to create a natural, undulating rock face type effect. Now, unlike the previous example, the heavy lifting here is really done by form and texture as opposed to color. The Maggie Centre in Aberdeen was designed to create a warm, nurturing, and supportive environment for cancer patients and their families. As a white concrete outer form resembling a pebble or a seashell. And it also features a prominent timber-lined entrance and is deliberately set into its landscape. I don't know about you, but I think this one really does achieve its design objective. It's like a cocoon or a nest. Completely differently, the humble Q Park in Sheffield, some of you will recognize, and it's known locally as the cheese grater. This is just a personal favorite of mine. And again, this one focuses now on form, and it's the apparently random repetition of a standard shape which strikes a balance between this chaos and uniformity to create real interest, particularly from a distance. Like it or loathe it, it's really interesting, and the parking spaces are really wide, so I like that one. So how is this all relevant to Benx? Well, I mentioned earlier our focus on innovation. At Zak in Birmingham last year, I announced the launch of our Safe Wall family of certified through-wall rain screen systems. The Safe Wall systems comprise all of the elements listed on this slide. From the decorative panels right back to the sheathing board, they're tested as systems and certified as systems. SafeWall's unique. As I said, the whole package is certified as a system. They're all A1 or A2 fire rated, so suitable for higher risk buildings. We provide all technical support through the Benx technical team. And we supply all of the components. We also train installers at the Benx Academy. And at the conclusion of the project, we provide a system guarantee comprising all components in a single integrated document. So the benefits of SafeWall are peace of mind, reduced complexity, and increased efficiency at every stage of the process, from design and specification through procurement and installation and ultimately ownership. So that's all very well, but how does that relate to what I started out by talking about? Well, currently SafeWall has 4 flavors, 4 systems in its family, with numerous finishes and color options. I'm just going to run through those very briefly. SafeWall with Swiss Pearl is an A2 rated system. Fiber cement panels in 90 standard colors. Similarly, SafeWall with rock panel is A2 rated. This time it's compressed basalt panels in over 200 colors, surface effects, and patterns. SafeWall with LuxClad is a system which is A1 fire rated, featuring solid aluminium panels, and they're available in any RAL color. And our most recent addition to the family is SafeWall with Clad Color, featuring our own proprietary fiber cement and calcium silicate panels. And again, this system is A1 fire rated. Clad Color panels are coated in-house in the UK, and they're available in a standard range of 45 colors, and we can color match any color subject to MOQ. We also offer Clad Color with a grain texture, and it can visually mimic natural stone. And we had a lot of interest recently from architects for Clad Color Natural as a potential substitute for GRC, particularly at height. It has considerable weight and cost advantages. So we have 4 SafeWall systems with almost limitless color options and many different textures and finishes. But we're not done yet. We plan now to integrate our slip-fast brick slip system into SafeWall. So that will go right back from the slips to the sheathing boards and the components in between. And then we'll integrate RenderClad. One of the great benefits of SafeWall is that on a particular building, you can combine these different facade finishes with relative ease, both from a design and installation perspective, because they rely on the same components behind the sheathing boards, making those interface points much easier to handle. So we believe it is possible to have all the benefits of a certified system approach while being able to select from a wide range of colors and textures to allow you to create facades that truly respond to human psychology and emotion. I've really only touched the surface of a very complex and really important subject. And there'll be many people in this room who know more about this subject than I do. I really wanted just to remind everyone of the importance of it. We cannot overstate the impact of facades on people. And I'm sure James this afternoon will add a lot of his experience and insights into this whole discussion. The significance of color, form, and texture choices is paramount in how facades are designed. I just want to finish with a quote. It's a plea from one of the great visionaries of modern design, Thomas Heatherwick, who is on a mission to humanize the built environment, to banish boring buildings. And he says, let's create buildings that are radically more human, buildings that people love and adapt, not hate and demolish. I certainly couldn't have put it better myself. Thank you for listening. Enjoy the conference, and please do stop by our stand for a chat. Thank you.
Thank you very much, Iain. Iain and the Benx team will be out next door after this, so please go and talk to them about colour, form, Photoshop and editing. Great, next up is Nick Backhouse from Proctor Group. Nick, please come to the stage. There you are. Sorry, I didn't see you there. The light's quite bright.
Okay, thank you. Good morning, everybody. Hope you're having a good day so far. Can you hear me? That's good, that's good. Okay, so my name is Nick Backhouse from the Proctor Group. I'm Business Development Manager for England North. Don't know if you've heard of the Proctor Group, but we're based in a small village up in a lovely Scottish village called Blairgowrie. We're a family-owned company, and we use heavily certifications to back our products up. So I've only got 10 minutes to speak with you about a really important subject that we've been kind of heard a lot about already today, condensation and airtight solutions for facades. So I will do my best to get through on time. So I'm sure you're all familiar with the BS 5250, the Management of Moisture in Buildings Code of Practice. I feel as though we're lucky enough to have this code of practice when we're looking at building design. I think one of the most important things, certainly for us, is regarding the breather membrane. Must be more than 0.12 meters SD. And that helps when we're looking at the holistic design for a building. Now, obviously, fire's kind of number one, but as I say, we do need to take kind of a holistic approach when we're designing the buildings. So we need to be looking at the building occupancy and weather. What's the building wanting to achieve? Are the rooms going to be multi-occupancy? Are we building high-rise, high-risk building? Is it going to be a student accommodation? So we need to really think about how many people are going to reside in that dwelling. Are there going to be more than 1, 2, 3, 4, 5, 6, 7 students in one room? Who knows? But we've got to think about really managing the moisture. If it's a care home, is the heating going to be on? About what we're going to do with that moisture and condensation. We also need to take weather into account. Are we designing a building in a coastal environment? Are we going to be in the middle of Manchester, Leeds? Obviously, within Manchester, we're building up now. So is the building going to be kind of battered by the wind and rain, driving rain? So yeah, obviously we need to think how we're going to manage all the moisture, heat and the air in line with the 5250. I think just to put emphasis on what I've mentioned, if you take anything away from my presentation today, I think it's the SD value with the membranes 0.12. So we're going to look at like a typical wall build-up now. I'm sure you'll be all familiar with this. So very quickly, we'll go from the inside. We've got the plasterboard there. We've got the internal VCL, the vapor control layer. We've got SFS, 100 mil of mineral wool. We've got the boards. We've got a membrane. And then we've got the helping hand brackets, 175 mil of mineral wool, and then the rails there. That's just to show you a typical. You might be familiar with that. So we're going to focus on the dwelling emission rates. You'll see at the end there. So we're going to look at a U value of 0.15. Air leakage would be 7. Dwelling emission rate 12.18. We're going to look to see how we can improve that, and I think that fits in well with today's subjects. So if we bring the U value down to 0.05, focus on sticking more insulation in, that might be a quick win, kind of an obvious statement really. But we'd leave the air leakage at 7. So that's actually a really good improvement, 6.7%. As you can see, the dwelling emission rates are down at 11.36 now. That's actually really good. But look what we've had to do to the insulation. We've had to put more insulation in, 630 mil. That's not really achievable, is it? It's going to be, the commercials. It's going to be extremely expensive. But also, if you're building in a city centre, you're not really going to have the footprint to bring the front of the facade forward. So the client's not going to be very happy because the yield of the property is going to be shrinking. So you're going to eat into the footprint of the building. So how else could we achieve a better dwelling emission rate? Okay, so there's a different way. It's been mentioned already before this morning, which is really good. As you can see, we've kept the U values the same. So we've used the original 100 mil SFS mineral wool insulation, 175 mil on the exterior there. But look at the air leakage, 0.5. It's actually overachieved by putting more insulation in, just by creating that airtight barrier with a membrane that's approximately 1 mil thick. But before I give you solutions, I'm just going to show you, obviously, traditionally, let's say, we used to have the airtight line on the inside of the room, okay? That's all good and well, that can be achieved, but you get penetrations through the internal AVCL. So as you can see, the tradespeople come in absolutely fine, but you do get penetrations. Sockets, lights, residents come in, start hanging the tellies up on the walls. Absolutely loads of stuff, really. Central heating, fans. So you're really destroying that internal airtight line. Okay, so Proctors, we do it a different way. Okay, as you can see, we've got a product called Wrap-Tight. Okay, this is how we achieve this on all our high-rise buildings. So Wrap-Tight, it's a self-adhesive. We bring it out to the cold side of the insulation, so it's not getting, the airline's not getting penetrated. Now, obviously, you're going to have your plenines, you're going to have pipe work, duct work. You can simply liquid flash around those penetrations, and it keeps the air within the building, and it keeps the dwelling emission rates high. It's a really good product. So it's self-adhesive, it's really easy to apply. You roller it on, lap it over, and that part of the building is airtight with immediate effect. It's got a W1 water holdout, so under construction, wrap it around your building, no rain's getting on through the membrane, okay? Obviously it's airtight, it's also vapor permeable, it's classed as an intelligent membrane. So it's really basic analogy, but you've got a goalpost, the air particles are the footballs, the vapor are little golf balls that you can throw through. So that's basically how it works. So we're really proud of this product, and it's kind of perfect for passive house projects also. So I think time's running on now. So just a few case studies just to show throughout the UK. We've got lots of staff on the ground. We can do kind of pre-construction assistance. We can do site toolbox talks for installation teams. So yeah, this is Kent Road in Birmingham, looking good in the sun. It's a shame to cover it up, isn't it? Don't you think sometimes? I think so. It's not football related colours either, just to let you know, or else I'd opt for claret and amber from Bradford City, but they wouldn't do it, unfortunately. But we've got Air Street in Sheffield. I was in Sheffield last night. It's protecting the building there. Huge project. Deptford Landings in London. Really high profile project. The airtight line was achieved really well on this project, actually. Manchester, Echo Street. Does anybody recognise that one? The towers. Obviously, the red membrane's covered up now, but yeah, that was a successful project for B&K. A project quite close to my heart. That's Sky Gardens in Leeds. It's a 30 plus tower block under construction at the moment. I regularly visit this site, working really closely with Air Façades and the installation team. It's a really proud moment, obviously keeping the air within the building once complete. I just want to kind of talk a little bit about this project. This is a Proctor project that we're extremely proud of, as well as all the others. It's called St Sidwell's Point, and it's the first passive house in the world leisure centre. I need to look at this because we achieved, when the building was complete, we achieved 0.1 air changes per hour. So we were really, really kind of pleased. So just to let you know, there was no internal VCL within that build. We managed it with the wrap tight on the cold side of the insulation. And there was a swimming pool within there as well. So we were really, really proud about that project. And just to let you know, 0.1 air changes per hour is on the whole of the building, I've been told, it's similar size to an A4 piece of paper, air leakage throughout the whole build. So we were really pleased with that one. I think that brings me to the end of the presentation. Look, it's a really important subject, so we do have a stand through in the other room. I'd love to continue the conversation if you're interested in the subject. Thank you for your time.
Nicking it. Yeah, as I say, Nick is going to be out there in a bit. Grab a tea, grab a coffee, grab Nick. He says it's way too big a conversation for 10 minutes. Right, next up, we've got Studio Egret West. We've got Lucy Head and Daniel Onions talking about variety of projects, all Manchester-based, Mayfield, Albridge House, and Cotton Key. Sorry, I forgot about that one.
Okay. Sorry. Studio Egret West is a transdisciplinary design studio. We design and curate places with compelling narratives and identities, places that are firmly rooted in their context and grow naturally out of it, places that cultivate sustainable communities, amplify and prioritize the public realm, and evolve over time. We've distilled our way of working down to a list of S's. Some have formed part of our mantra since the early days, and some have become more important as the years have gone by. We have designed thousands of new homes across different typologies and tenures, have over 10 million square foot of built workspace in current development, have built over 55 acres of public open space, and have over a dozen cultural venues underpinning cultural ecosystems in sustainable neighborhoods. After 21 years, we know what we are good at, which is shaping everyday wonder. This approach has defined our ongoing commitment to Manchester. Over the past decade, we've had the opportunity to work across the city at multiple scales, from individual buildings and public spaces to large-scale regeneration frameworks and entirely new neighborhoods. Alongside this growing body of work, we also made the decision to open our own Manchester studio, embedding ourselves more deeply within the city and its future. Today, we want to talk about regeneration, not simply as development, but as the careful process of reconnecting cities to their histories, landscapes, communities, and futures. Manchester is a city that has always reinvented itself. From the Industrial Revolution to the digital age, its identity has been shaped by production, movement, infrastructure, migration, and innovation. The question is no longer simply how we grow, but how we grow sustainably, inclusively, and meaningfully, and how that growth is expressed, experienced, and made legible through architecture. Facade discussions often focus on performance, systems, and enclosure, which are obviously critical. But across these projects, we became increasingly interested in the facade as something larger, a mediator between landscape and city, between industrial memory and contemporary life, and between private buildings and public experience. Across Manchester and Salford, our work explores how architecture, landscape, ecology, and urban design can operate together to create places that feel rooted in their context while responding to the pressures of a rapidly evolving city. What connects these projects is a shared belief that successful regeneration is not about isolated objects, but about continuous urban frameworks where buildings, facades, landscape, infrastructure, and public realm operate together as part of a single civic experience. These are places where communities can form, public life can flourish, and nature becomes part of the everyday urban condition. Oh, sorry.
All right. Okay. So, Cotton Key. Across Greater Manchester, some of the most significant regeneration opportunities are emerging not from vacant city centre sites, but from former industrial infrastructure that once powered the region's growth. Cotton Key represented one of those such opportunities. Located within Salford Quays, the site was once central to one of the largest infrastructure undertakings in England, bringing ships carrying cotton directly into the heart of industrial Manchester. Yet despite this remarkable history, Much of the area today is occupied by surface car parking and fragmented leftover space. The vision for Cotton Quay seeks to transform this dormant waterfront into a thriving mixed-use neighbourhood centred around water, landscape, ecology and public life. The proposals will deliver almost 1,500 new homes alongside hotels, leisure facilities, restaurants, community amenities, and a network of public spaces that reconnect the people to the waterfront. Rather than treating the water basins as remnants of the past, they become the organising structure of the master plan and the catalyst for a distinctive place identity. At the heart of the vision is a commitment to creating an active and accessible waterfront. A new south-facing promenade extends along the length of the site, connecting key destinations and encouraging movement between the Metrolink network and Central Bay. Animated by cafes, restaurants, and public activity, this promenade transforms what was once fragmented infrastructure into a vibrant civic edge. The landscaping strategy celebrates the unique character of these former docks while introducing new ecological and recreational activities. 3 historic basins establish a new relationship between residents, visitors, and the waterfront. Throughout the scene, the architecture and landscape are designed as a unified experience. New residential buildings, hotels, public spaces are carefully arranged to maximize daylight, views, and access to the water. Building heights step across the site to maintain sunlight penetration into streets and public spaces, ensuring that the waterfront remains welcome and active throughout the year. Like many of Manchester and Salford's most successful regeneration projects, Cotton Quay draws from strengths of its industrial heritage without seeking to replicate it. Instead, reinterpreting its character of the docks through contemporary forms, public spaces, civic infrastructure that support modern patterns of living, working, and recreation. Ultimately, Cotton Quay demonstrates how former industrial infrastructure can be transformed into a contemporary waterfront neighbourhood. It is a project that celebrates the legacy of Manchester's industrial past while creating new opportunities for living, leisure, and community life alongside one of Greater Manchester's most remarkable waterfront settings.
Holt Town. Holt Town represented a broader opportunity to reimagine an entire district in Manchester as a new urban neighbourhood. Situated along the River Medlock between Ancoats, New Islington, Sports City and the Etihad campus, Holt Town occupies a strategic position within the city's growth corridor. Once defined by industry, infrastructure and fragmented development, it now presents a rare opportunity to create a new community that reconnects people, nature and heritage. The ambition for Holt Town extends beyond housing delivery alone. While the framework has the potential to deliver around 4,500 new homes, including affordable housing and a diverse mix of tenures and typologies, its deeper objective is to establish a distinctive model for urban growth, one that places landscape, ecology, and community at the centre of regeneration. At the heart of the vision is the idea of a woodland town. Inspired by the layered structure of woodland ecosystems, this framework proposes a neighbourhood that grows organically through interconnected layers of landscape, movement, heritage, and development. This analogy provides a structure for understanding how the district can evolve over time while maintaining a coherent identity rooted in place. Rather than treating nature as an addition to development, the landscape becomes the framework upon which the neighbourhood is built. New parks, green streets, ecological corridors, and public spaces work together to create a connected network that supports biodiversity, climate resilience, and everyday life. This approach is reinforced through the concept of a sponge town, a neighbourhood designed to work with natural water systems rather than against them, sustainable urban drainage, enhanced river canal environments, extensive tree planting, and integrated blue-green infrastructure help manage flood risk while creating healthier and more attractive public spaces. Importantly, Holt Town is not conceived as a tabula rasa development. The framework seeks to reconnect this part of Manchester to its industrial heritage, retaining and celebrating existing assets where possible, while creating opportunities for new forms of living and working. Like many of Manchester's most successful regeneration projects, it looks forward while remaining grounded in the character and history of the place. The process of creating the NDF engaged a wide variety of landowners and occupiers, including the City Council, in a highly collaborative process. This engagement was crucial in forming a master plan that reflected the ambitions and views of all stakeholders, fostering a sense of shared ownership and commitment to the project's success. Ultimately, Holt Town demonstrates how regeneration can operate at the scale of an entire ecosystem, not simply creating new buildings, but establishing the ecological, social, and spatial foundations for a resilient urban community. In many ways, it represents Manchester's next chapter of growth, landscape-led, climate-conscious, and deeply connected to the city's industrial legacy.
Albert Bridge House. Another reoccurring theme across our work in Manchester is the rediscovery of its waterways. For decades, many of the city's river corridors become disconnected from public life, hidden behind roads, surface parking, and fragmented development. As you can see here on the right, the major gateway between Manchester and Salford, the site was historically dominated by an inaccessible mid-century tax office building and extensive surface parking. These structures created a physical barrier along that river edge. Removing this concrete obstruction, the project unlocks the opportunity for an entirely new public landscape, transforming the site into a generous, coherent riverside realm framed by residential towers, workspaces, shops, cafes, and ecological planting. Importantly, the landscape here is not conceived as residual or leftover space between the buildings. It acts as an organizing principle of the entire project, shaping how the architecture sits within the site, how people move through it, how the development reconnects back naturally to the surrounding urban fabric, the river, the landscape, and the wider city. As people move through the public realm, the architecture reveals a constantly changing sequence of views, allowing the development to be experienced from multiple perspectives rather than as a singular object. The arrangement of these buildings is equally important. Rather than forming a continuous edge, the towers are positioned to create visual permeability through the site, opening up new sight lines towards the city. At the center of this scheme sits an urban arboretum where hard surfaces give way to planting, rain gardens, and meandering pathways. Along the river edge, we have an elevated steel mesh walkway. This negotiates the level change down to the River Irwell. More than simply a route through the site, the structure becomes an extension of the landscaping itself, projecting outwards over the river corridor and creating a new point of connection between the city and the water. From here, visitors are brought closer to the river than was previously possible, opening up new views along the Irwell and reinforcing the site's relationship with that waterfront. The scheme brings forward a wealth of residential, commercial, and amenity uses, creating diverse, complementary mix of homes, workspaces, leisure centres, social spaces. Collectively, these elements support a vibrant, self-sustaining neighbourhood where daily life, work, and recreation are woven together through a landscape-led approach to placemaking. Although conceived as a family of 3 buildings, each volume develops its own distinct architectural identity. The residential tower facades are articulated through scalloped metal panels whose curved profiles catch their light, shadow differently throughout the day, giving the elevations a constantly changing depth and texture. In contrast, on the right, the commercial workspace adopts a more ordered expression, organized into horizontal strata. These layered bands expand as the building rises, beginning with tighter groupings at the lower levels before elongating towards the top to emphasize the verticality and slenderness. While these buildings offer different architectural expression, they are united through a shared family of materials and tones. The residential towers draw directly from the rich reds, rust, coppers associated with Manchester's historic industrial architecture. The colour palette shifts subtly, vertically, with deeper reds, darker tones, grounding the lower levels, gradually transitioning towards lighter bronzes and coppers as the buildings rise into the skyline. The commercial workspace adopts a warmer bronze palette that complements the residential towers with its own establishing its own character. The commercial facade is organized around a series of clear design principles. The regular structural grid provides order and consistency across the building. While the grouping of floors gradually changes as the tower rises, this visually elongates the building towards the skyline. The relationship between solid and transparent elements also shifts vertically, creating a facade that develops in character from the base to the top, rather than repeating a single module across the entire elevation. These elevations show how the environmental performance directly influenced the facade design. The south-facing elevations became more solid and protective, incorporating a great proportion of shading elements to reduce solar gain during peak hours. In contrast, the north-facing elevations become more open, transparent, maximizing access to softer natural daylight, improving the quality of these internal working environments. Rather than applying a uniform solution, the facade responds directly to the orientation of daylighting and environmental conditions. The commercial building incorporates a series of carefully positioned windows that establish visual connections with key routes and destinations across Manchester and Salford. These openings interrupt the regular rhythm of the facade, introducing depth and variety while helping orientate the building within the wider city. At ground level, the building adopts a more recessed and slender base, allowing the landscape and public realm to extend naturally into and around the building, creating an open and more welcoming pedestrian experience. The residential towers develop a different architectural language. Emerging from the same octagonal geometry, the facade is organized around a vertical rhythm that reinforces the slender proportions of the towers. The scallop facade system introduces depth, shadow, and variation across the skyline, while gradually transitioning in color helps lighten the buildings as they rise into the skyline. Together, these elements create facades that appear both sculpted and responsive to changing light conditions through the day. At street level, the architecture deliberately softens and opens towards the public realm. Exposed structural columns create sheltered colonnades and active frontages, while vertically articulated masonry draws influence from Manchester's historic architecture. At Albert Bridge House, the facade is not simply treated as an enclosure or surface expression. It instead becomes part of the wider environmental and urban system, responding to the river, responding to light, responding to climate, responding to the movement, responding to public life. In this way, the facade is not just an object, it's moving towards the facade being a civic interface.
Perhaps nowhere illustrates Manchester's transformation more clearly than Mayfield. For decades, this area beside Piccadilly Station remained largely forgotten, an extraordinary post-industrial landscape hidden in plain sight. Yet beneath the neglect was an incredibly rich history: textile production, rail infrastructure, warehouses, engineering, and industry layered over generations. The regeneration of Mayfield began with a simple but transformative idea: reconnect the city to this forgotten landscape rather than viewing the site's industrial legacy as an obstacle. It became the foundation for a new piece of city, one shaped by heritage, culture, ecology, and public life. The reopening of the historic depot in 2019 became an important catalyst, recognizing the importance of creating activity from the outset and understanding that regeneration on this scale takes time. The salvage depot building became the centerpiece of Mayfield's meanwhile strategy. Rather than waiting years for the master plan to emerge, cultural uses activated the site immediately. Today, the depot hosts award-winning events, food markets, exhibitions, and community programs, helping establish Mayfield as one of Manchester's most exciting destinations, while creating public ownership long before the first homes or office buildings arrive. At the heart of the wider master plan sits Studio Ego West's Mayfield Park, the first new city centre park in Manchester for more than a century. The 6.5-acre park has transformed a previously derelict area of the city into a biodiverse expanse of green and blue infrastructure. Crossing the line between civic space and urban garden, the park is a vibrant mix of water and wetlands, trees and wildflowers, long lawns, play areas, and rain gardens, combining biodiverse ecological areas for wildlife with recreational space for visitors, all inspired by the site's rich industrial heritage. Importantly, the park is not conceived as leftover green space between buildings. Instead, the entire master plan evolves from the landscape itself. Delivered first, every development parcel, every route, every public space will be organized around the park itself. As Mayfield continues to grow, the relationship between architecture and nature becomes increasingly integrated. Rather than placing buildings on the edge of the park, the ambition has always been to create buildings within the park, architecture that feels like a natural extension of the landscape. As master planner, it was important that Mayfield avoided becoming a singularly created environment with one dominant architectural language. Working alongside Bennett's Associates, Morris & Company, and Shed KM, the ambition has been to create a neighbourhood with richness, variation, and character, reflecting the layered and incremental nature of Manchester itself. Like the city, Mayfield should feel as though it's evolved over time rather than being delivered in a single moment. Today, Mayfield is defined by an eclectic juxtaposition of structures, materials, and textures. Railway viaducts sit alongside steel infrastructure, brick warehouses, landscapes, and contemporary interventions. It is these layers that give the site its unique atmosphere and identity. Understanding and celebrating those layers becomes fundamental to the design approach across the master plan. This informed a site-wide approach to materiality. The new neighbourhood draws directly from the colours, textures, and robustness of the retained industrial structures. Rather than replicating history, the architecture reinterprets it through contemporary forms and construction techniques. Durable materials are prioritised throughout, creating buildings that feel robust, grounded, and capable of aging gracefully alongside the existing fabric of the site. The colour strategy emerges directly from the depot itself. Parcels on the western side of the park draw from the darker greys and greens of the steel railway arches, while parcels to the east take cues from the warm red tones of the brick viaducts and arches. Together, they create a family of buildings that feel distinct yet connected. This strategy is reinforced through a simple architectural framework. In the foreground, a collection of lower-rise buildings establish a rich and varied park edge. Inspired by Manchester's historic warehouses, these buildings use warm tones, distinctive roof lines, and strong geometric forms to create character and identity at a pedestrian scale. Behind them, a family of taller buildings contribute to the emerging skyline. These towers are intentionally lighter and more restrained, allowing the architecture closest to the park to remain the primary focus of everyday experience. A continuous datum ties these elements together, drawing from the monumental scale of the railway arches and infrastructure that define Mayfield's industrial character. At ground level, this datum creates a consistent rhythm of entrances, commercial uses, and public activity at the park edge. The first residential phase, Chapel Field, brings these principles into built form. SEW's scheme takes its name and inspiration from Chapel Field Works, a collection of industrial warehouse buildings that once occupied the site. These buildings combine straightforward industrial structures with moments of civic ambition and architectural expression. Functional workshops sat alongside distinctive landmarks, creating a rich and varied industrial landscape along the southern edge of the River Medlock. Our residential proposals reinterpret that character for a contemporary neighbourhood. Simple, robust forms and a carefully composed palette create a family of distinctive buildings overlooking the park. Rather than reproducing the architecture of the past, the design seeks to capture its spirit, creating homes that feel inherently Mancunian, rooted in the site's industrial heritage while looking confidently towards Mayfield's future. From the outset, we understood that delivering the architectural quality we were aiming for would require careful balance of ambition, budget, and planning impact. Working closely with the wider consultant team, we developed a facade strategy that concentrated investment where it would have the greatest public impact. Given Mayfield's prominent position with views from the park, Mancunian Way, and the wider city, the outward-facing elevations were prioritised. The arrival building takes its inspiration from the former entrance building on Chapel Field Works, acting as a marker for Mayfield's first residential neighbourhood. To establish a distinct identity along the park edge, we proposed a material language that contrasted with the surrounding brick buildings. Faceted GRC panels provide subtle variation in colour, texture, and depth, creating a highly crafted yet robust architectural expression. Alongside this sits a more robust brick volume inspired by the simple industrial buildings that once occupied the site. Its sawtooth roof line references former factory buildings and creates a distinctive silhouette within the park. Large punched openings with deep brick reveals reinforce the building's warehouse character, while Juliet balconies allow for the facade to maintain a simple and consistent rhythm. The building is elevated on steel supports, allowing the landscape to extend beneath and strengthening the connection between architecture and parkland. The two residential towers were conceived as a family of slender brick buildings with a functional yet elegant architectural language. While sharing common design principles, subtle variations in materials and detailing help distinguish them from one another. The facades establish a clear visual hierarchy through strong vertical proportions, regular rhythms, and careful balance between solidity of brickwork and the reflectivity of perforated metal panels and window frames. A key feature is the alternating splayed perforate purge panels, which create movement and variation across the elevations while reinforcing their vertical emphasis. Within the internal courtyard, the facade strategy becomes deliberately more restrained, reveals are simplified, facade depth is reduced, and the purge panels become flush with the brickwork. This allows resources to be concentrated on the elevations most visible from the park and wider city, while maintaining a constant architectural language across the development. The most prominent elevation faces Mancunian Way and therefore carries the richest level of articulation. A rhythm of slender masonry piers and recessed two-tone brickwork create depth, shadow, and a strong visual hierarchy. Narrow window openings and integrated perforated panels help manage solar gain while reinforcing the building's vertical proportions. The result is a facade that responds simultaneously to environmental performance, long-distance views, and the architectural character established across the wider Mayfield master plan. Chimneys were an integral part of the industry and dominated the landscape and skyline of Manchester. These vertical structures have been reinterpreted as vertical balcony stacks on the buildings, which will be prominent features on the facade. The largest of these chimneys balconies serves as an external amenity to the residents' shared dining room. As the first residential phase within the master plan, Chapelfield marks the next chapter in Mayfield's story. These buildings are not conceived as standalone objects, but as part of a much larger landscape-led vision for the future of the city. And in many ways, they embody the central theme we've explored throughout this presentation: architecture shaped by context, informed by heritage, and integrated with landscape to create places that evolve over time.
I've got 13 seconds. Manchester's industrial heritage provides an extraordinary foundation for its future, but the city cannot rely on nostalgia alone. It must reinterpret that legacy through new forms of urban living that prioritize sustainability, inclusivity, culture, and well-being. Across these projects, we've explored how landscape, infrastructure, architecture, and facades can work together as part of a shared civic framework. In many ways, Manchester is regrowing itself, and perhaps the most important lesson from these projects is the future of cities is not only about what we build, but about the relationships we create between heritage and innovation, architecture and ecology, people and place. Thank you very much.
Thank you.
Thank you very much, Lucy and Daniel. Quite an array of place-centred development going on there in Manchester, and well done for being at the heart of so much of it. That's us to a break now. We're back at 11:50, so go grab a coffee, grab a tea, go and talk to a Proctor group and to Benx, and yeah, we'll see you in a bit. Could I also invite the speakers this morning to come to the stage, alongside Andrew? Andrew from Novastruct as well, to present some mementos. Thank you very much. Hello, everyone. Session 2. Right, without further ado, I suppose, take Liverpool, fantastic set of buildings. This is 6A Architects, John Ross and Chiara Faliva from Bureau Happold to talk about what they're doing there.
Morning, thank you very much for that welcome. So yes, I'm John Ross, Director at 6A Architects, and
Chiara Faliva, Associate Director at Bureau Happold, Facade Engineering.
A quick introduction to 6A Architects. We were formed in 2001. We're based in London and work across a variety of projects, including residential, commercial buildings, but a really core part of the building's work has been in cultural and arts projects, often working within existing buildings and heritage environments. Some of those recent projects include the extension of MK Gallery in Milton Keynes, the Centre for Art Research and Alliance, which is in a former card-playing factory in New York. And kind of most recently, we've completed the decarbonisation and restoration of Skinner's Hall, which is a Grade 1 listed scheduled monument in the City of London. To Chiara?
Bureau Happold Facade Engineering, I guess you know us. We are these places around the world. We also have an office in Manchester. And yeah, then I'll do that. Yeah, thank you. You know, we cover all services related to facade engineering, and this is just you know, a range of different projects that we work recently. But let's talk about the project.
Yeah. So we are currently working over in Liverpool for the Tate Gallery. This is our project, reimagining the Tate. We've been working on this since about 2022, when we were appointed for a kind of once-in-a-generation transformation of the gallery. Now, Tate Liverpool is located on land reclaimed from the River Mersey by Victorian engineers. It was designed by, the buildings were designed by architect and engineer Jesse Hartley, who designed the Albert Dock and the surrounding buildings, and these were opened in 1847. The new dock in the center was surrounded by a series of really kind of novel and innovative fireproof warehouse buildings. The dock and the warehouses were built from a robust palette of granite and brick. Hartley was the son of a stonemason. And internally, you have these absolutely fabulous structures, hollow cast iron columns, curved cast iron beams, and brick-jack arch floors. This is a view from 1920. The dock was closed to commercial shipping in 1927. But then the warehouses continued in use for goods storage through the Second World War, and then they were gradually emptied in the 1950s. The warehouses were vacated. The area fell kind of victim to vandalism and neglect, but at the same time, the Albert Dock was listed for the first time, Grade 1 listed in 1952, as the earliest enclosed docks in the world and a complete example of the type. So through that process of being abandoned and neglected, the docks silted up, and they remained unused and completely closed and derelict until the 1980s, at which point there was a kind of process, a kind of citywide process across Liverpool of regeneration, which started with the process of bringing water back into the docks, and then the restoration of the derelict buildings of the dock quickly followed that. And one of those warehouse buildings at the northwestern corner of the dock was identified to become home of the Tate in the North in 1988. This was the first Tate gallery outside of central London. And the competition to design the gallery was won by James Sterling and Michael Wilford, and that kind of followed on from their completion of the Neue Stadt Gallery in Stuttgart, which they did in 1984. And then the Claw Gallery for the Tate in London in 1986. And this was a really kind of passion project for Sterling. He was raised and educated in Liverpool. These are his photographs from his time as an architecture student in the city in 1947. So he kind of really enjoyed the kind of muscularity of the architecture of these buildings, and kind of watched them through their period of post-war decline. The Sterling and Wilford project saw both the restoration of the Hartley building and the carving of some really significant new vertical circulation routes through the building. So we have kind of restoration of the historic roofs, introduction of new roofs, and then these kind of carving of these big stair and lift voids that went all the way up through the existing building. In doing so, they quite kind of dramatically shifted the character of the existing kind of Jesse Hartley plan, which was very open, and they made a series of spaces that were kind of slightly more internalized. The new gallery announced itself with a facade of orange and blue along the kind of dock elevation, and that opened internally into this kind of double height foyer. All the way through this project, they kind of really celebrated the material character of the historic warehouse. And they created a series of gallery spaces that was carved through this really heavy industrial architecture. So double height spaces on the ground floor and on the right, and more compressed kind of lower gallery spaces on the upper floors of the gallery. And there were a series of interventions that happened, and we'll talk a little bit more about them as we go through in both the 1990s and in the 2000s that kind of tinkered with elements of the scheme that were more problematic or operationally challenging. But the primary moves of the Sterling scheme remained intact when we won the project and were appointed in 2022. Which then brings us to the present day. We're about 18 months into construction, and we're aiming to complete the works in mid next year. One of the first moves that we really wanted to make with the project, a kind of consistent ambition, was to open the gallery up to the city, to really break down barriers to entry and make the life of the Tate visible to the public in the city. As another element of that, it gave us the opportunity to open up the interiors of the gallery spaces to this extraordinary landscape of the River Mersey that the west-facing elevation looks out onto. We've been seeking to restore some of the sort of clarity of the original Jesse Hartley plan in the top left-hand corner, and To do that, we're creating a new art hall at the ground floor that will welcome visitors. It'll host art exhibition space, shopping, coffee, space for kind of socializing, large kind of public performances and events. The space through that kind of ground floor, this is a working model that we use through consultation. It's very kind of open and public. The ground floor includes this gallery shop, and then this kind of robust materiality of the existing brickwork and cast iron is expressed and celebrated and enjoyed all the way through. New vertical circulation is carved out of the building, and that connects the ground floor art gallery, the ground floor art hall space as you come through with the galleries above. And these are some of the kind of really careful structural interventions that Bureau Happel structural engineering team have been working on to allow us to make these new openings for staircase and lift carved through the curved cast iron beams and these extraordinary brick vaulted floors. Always, we've designed these new points of vertical circulation so that they're always giving a view back to the city. On the upper floors, we then have a series of climatically controlled galleries that overlook the dock to the west. And also the whole top floor, the galleries are being quite lightly refurbished all across the top floor. And then facing out west onto the river, we have a series of kind of riverside foyers, education spaces, and a cafe that will now have these kind of fantastic views out across the River Mersey. Which then brings us to the kind of facade project drivers. And really the reason we're here to talk today is about why we see there's an important space for kind of technical facade engineering in a historic building context. So the things that we were trying to do, we were trying to increase the kind of visual permeability of the facade. We wanted to open up the ground floor to improve accessibility and usability. We wanted to improve the envelope in terms of its thermal performance, and wherever possible, in non-gallery spaces, we wanted to introduce natural ventilation. So then the first kind of technical challenge, and probably the most significant technical challenge we faced, was how we dealt with the insulation of historic monolithic masonry. And that's part of a much bigger sustainability narrative that sweeps across the project, which addressed the fact that the energy performance of the existing building was kind of really poor. The gallery set very ambitious targets for improving the operational energy performance of the building in accordance with its own kind of policy directives set out by Tate Declares. And so really the challenge for us as a design team was how you go about upgrading a building with this very particular material character of solid, heavy masonry walls in a way which works with the very particular character of the historic building fabric and in accordance with kind of best conservation practice as led by Historic England. It's worth saying that all of this is sort of this broader energy strategy is complemented by a shift from gas boiler heating to a water source heat pump solution that's being installed within the Albert Dock Basin to provide, to effectively remove fossil fuels from the site. So one of the first conversations that we had with Bureau Happel, and at this point I'll hand over to Chiara, but was really how we address this approach of upgrading the U value of the existing building, and we looked at what the Stirling and Wilford team had done with the introduction of painted VCLs onto the brickwork and mineral wool linings. We looked at what might be a more kind of common case to use a mineral wool lining and a new VCL internally, and then we looked at an insulating lime plaster solution. And using a kind of breathable insulating material that could work very naturally with the character of the existing buildings.
Okay, so we initially started doing some quite common thermal analysis on the conventional options. So there would be mineral wool insulation with the cavity placed in different locations within the build-up. We identified the risk of condensation within the cavity. We also analyzed the embodied carbon for with the different options, and we found out that the second option, which was the mineral wool fixed to the brick with internal lining and VCL, was equal to the insulating lime plaster and the wood fiber internal lining. So after considering all of the different options, as John mentioned earlier, we identified that we really wanted to go with the insulated lime plaster and the wood fiber directly applied to the internal side of the wall. This again because it's very breathable, it reduces the risk of interstitial condensations, and also in terms of application, it reduces the trades involved, it reduces the different types of materials, and the embodied carbon was something that we were happy with. But obviously, this didn't remove the fact that there were some residual challenges. So there is still a risk of interstitial condensation. There is still some limits to the moisture content on these materials, and we had to work within the achievable U values. And how we solve all these challenges through U value measurements, material testing, hydrothermal analysis, and material selection. We also wanted to fine-tune the thickness of the internal insulating plaster with the thickness of the walls. Obviously, we have quite thick walls at the base. They become quite thinner, 450 millimeter at the top. So we identify the right thickness of the insulation based on the thickness of the wall. We measured, because we wanted to have an accurate baseline, so we measured the U values with sensors. We found then the U values exactly measured, so we used that as an input in our analysis. But also we wanted to know a little bit more about the bricks themselves, because we wanted to input correct information and data into the WUFI software for the hydrothermal analysis. So we carried out some physical testing, like water absorption on the bricks. So this is the WUFI analysis, the results. So we initially tested the 450 millimeter brick wall, which is the thinnest one because it's the one most at risk for interstitial condensation, because it's the more exposed to wind-driven rain, so there will be an increased moisture content. And we analyzed the 40 millimeter plaster plus 60 millimeter wood fiber, and we found out that there was a fail, so there was condensation forming at the interface between the plaster and the brick interface. So what we did, we did a further analysis reducing the thickness of the plaster, and we had positive results. So we identified that a maximum of 40 millimeter insulation at the thinnest wall was the one that was actually successful. We carried out analysis on the different thicknesses to identify the correct thickness of insulation. And just briefly to go back, obviously by reducing the amount of insulation in the thin wall, we always had an increase of the U value. So there was throughout the project coordination and a feedback with the MEP engineer, with the sustainability consultant, to really find and fine-tune the strategy and size the MEP. Oh no, I'm going backwards. So so the final design proposal, at the end, we decided to get rid of the wood fiber for a series of reasons, including that it's not a very durable material, especially not very resistant to impact in a public space. But also we wanted to reduce as much as possible the trades and the materials involved and make the installation as quick and streamlined as possible. And the table below shows, how the different thicknesses, for different thicknesses of the existing wall, we identified the most effective thickness for the insulation. So we went from 40 millimeter to 60 millimeters, depending on where we are. We had to work out detailing after defining the base design. For example, the reveals have a thinner layer of insulation because we need to stay within the line of the existing windows. And then On the right-hand side, you see that, yes, this detail. So the plaster stops short at the top of the wall to make advantage of that thermal bridge, which is caused by the embedded cast iron. So because we didn't want again condensation forming around the embedded element. These are some images from site recently of the insulation being installed. Obviously, we had to prepare the walls, both internally by removing the existing finishes and also identifying moisture and water ingress, so fixing wherever we had cracks or instances of water ingress by repairing the facade. Repointing and replacing bricks were needed. There's also a nice story about brick reuse, because we had to demolish and open up some of the bricked up openings, and the bricks were cleaned and reused on site for repairs, but also for making these, they were sliced and then formed to make pavers for the new stairs. So there's also a nice, example of reusing, and some pictures from site showing the insulating plaster being installed. On the right hand, the picture that shows the lining that is installed in front of the insulated plaster in the gallery spaces, because that was the requirements. But we also took advantage of that space, that cavity, which is almost 1 meter wide, to hide services behind. We're going to talk about windows quickly.
Yeah. So beyond the installation of the external masonry, there's obviously a process of trying to upgrade the performance of the existing windows. We wanted to extend the life of the existing metal windows by repairing them. We wanted to open up the cargo doors, which had been kind of blocked in, and there were a series of bricked up windows. We wanted to improve the overall thermal performance whilst reducing the risk of condensation. In some places, we wanted to allow those windows to open for natural ventilation. And there's underpinning all of this, there's the kind of heritage pressure to match the visual appearance of the existing slender frames of the windows. These are the windows before the 1980s, so you had a series of cast iron windows which had deteriorated incredibly badly through neglect, but also because this is a very harsh marine environment. So in the 1980s, they cast a series of aluminium windows as a sort of more robust and long-term solution that relatively faithfully replicated the original condition. But they had been sort of gradually blocked up behind, had slightly awkward secondary glazing installed that was visible through the outer frames. So the first thing has been just a very straightforward process of repair, reglazing, reputtying of the glazing. But then the next thing was to unpick the sterling, some of the limitations of the kind of sterling Wilford detail of these kind of fixed bits of secondary glazing that you can see on the left-hand side, which had given problems with condensation, that you can see on the right-hand side.
So the engineering input regarding the windows, obviously we carried out, usual thermal analysis, but with the aim of refining the U values, always in coordination with the MEP. So it was a fine-tuning exercise, and optioneering of the interfaces. Obviously, these are cast aluminium frames, so highly conductive. So there was a high risk of condensation at the interface. These are not, the window is not just a window, so we had to also deal with location-specific performance requirements. Obviously, barrier loading, a lot of these windows are quite low on the finished floor and are in public spaces, but also we had to provide UV light protections in the galleries and also deal with the G value. Again, a balanced approach. We wanted to maintain the clarity of this glass, the vision inside and outside the building, still balanced with the heat gain. And one piece of unusual analysis that we've done, so we observed that there was risk of condensation within the cavity between the existing window and the secondary glazing. So how we approached that, we carried out a sort of like a microclimate analysis using EIS software to identify what was the minimum ventilation gaps that was needed in the existing window to allow this excess of moisture to evaporate and ventilate. It was an issue before because we observed ice on these windows. So this was quite an important piece of analysis. So we identified exactly the right portion. Here are some details.
Yeah. Generally, we have two different types. We have two different conditions. We have sealed windows, which are specifically in the climate-conditioned galleries and some of the other climate-controlled spaces where we are keeping the existing windows, but then installing secondary glazing internally. It's openable, so it can be maintained. But then also to the big cargo doors, we're introducing a series of double-glazed aluminium frame windows. But the ground floor spaces in particular, this kind of open art hall, we really wanted that to be a naturally ventilated space, a passively ventilated space. And there was this challenge of trying to meet the kind of conservation constraints of dealing with this kind of slim expression, which we worked through with the planners. They didn't like the proposal to use planted mullions, which is what we had initially proposed. They sort of didn't find that there was a sufficient depth of expression in the glazing bars. So what we've done instead is remove the glazing, remove the glass from the original window frame. The frame remains intact, and then the thermal line and the water line is moved inboard with a slim steel window section, and combined with new steel doors that open out onto the public courtyard of Mermaid Court. Really, the building is just now, this is 2 weeks ago, starting to kind of deliver on that initial promise of these much more open views from the circulation spaces out across the city and out across the river. So it's very exciting to see that sort of starting to come into being. And then really the final thing we wanted to talk about was a very different type of heritage and how you deal with 20th century heritage, and specifically the work of Jim Sterling. Sterling had introduced this new facade of kind of blue and orange, quite pop along the kind of main colonnade elevation. But it was quite it throughout its life presented various problems in terms of openness and accessibility, and it was also completely fixed. There was no opportunity for natural ventilation. So what we wanted to do was to take parts of that scheme that were kind of really important, maintain them, adapt them, and make the facade work. So this is Sterling's original drawing for the facade, and then it underwent through the 80s, 90s, and 2000s a series of interventions that gradually opened it up. So when we took the facade on, we still had plenty of components of the original Sterling facade, these kind of orange drum doors, the kind of blue cladding panels, and then also elements of the 1980s work done by his partner Wilford. They were both a sort of add-on curtain wall system using similar but not exactly identical detailing. And really our proposal has been to take and reuse the remaining panels from the Sterling facade, move them to one end of the building, and then open up the facade at the north end into something much more permeable, much more visually open, and in many ways much more in keeping with the original Hartley dockside elevation, which really opened onto the waterfront. So from left, you have the conserved Sterling panels. On the right, a new curtain walling system with inward opening ventilation. It's all painted in the same cast iron, in the same dark color as the cast iron structure. So there's a sense of ambiguity between inside and outside, and retaining that sort of that earlier sense of the open dock front. I think
very quickly, the engineering input was about, again, thermal analysis, reducing the risk of condensation, but also adaptation by creating also and allow the ventilation of the cavity, and studies on the embodied carbon for material reuse options. And yeah, these are the steel being reused, and the panels being repaired, And just the last slide is about the conclusions, some lessons learned from this project. It's so important to assess, analyze, and testing in existing buildings is so critical to then provide balanced solutions that are not detrimental to the building, but they're still achieving the project targets. And I think I'm going to close there.
Thank you, John and Chiara. For any that know that building, the work that's being undertaken there is quite fantastic because it's a very introverted building and it's always looked inwards on itself. And actually to open to the river and to the sort of pier elevation is really quite exciting, I think, for Liverpool to give it a front door and a view out. It's really, really fantastic. Alongside the rigour which Bureau Happold have put into the facade testing and how you get the right answer is really impressive. But onwards, Novastruct, Andrew is here to talk about your systems. And Manchester, sorry, come up.
Hi everyone. I'm Andrew, the marketing lead at now Novastruct. Unfortunately, our technical director, Gary, couldn't make it. So hopefully you can put up with my voice and not his nice, soothing Yorkshire mellow tone. But I'm grateful to have the post-cake slot. So hopefully you're all feeling a bit sleepy, which might make this go a bit smoother. You may still be wondering who are Novastruct, but you will know who this is and our projects, because Cornier is now Novastruct. We recently rebranded Cornier Europe to Novastruct, continue our legacy across 3 strategic locations in Europe, France, Netherlands, and of course, the UK, laying stronger foundations for us as a systems house in the UK and Europe. And our specialty is aluminium curtain walling, windows, and doors. Thank you to Zak for having us as presenting partner in Manchester, providing the platform to share the rebrand with architects, specifiers, and consultants. We have a rich history of supporting facade elements in Manchester's growing skyline, and it's a great location to have Zak's 219th edition in partnership with Novastruct. I'm sure you've all seen this image, and it may be in more presentations today, but Manchester has become one of the UK's most active proving grounds for ambitious, high-density and design-led facade solutions outside of London. The city is not just growing, it's becoming more architecturally demanding. That's something I want to stick with you after today. Manchester is one of the clearest examples outside of London where the facade design is becoming more complex, more performance-led, and more central to architectural identity. But don't change too much. And we know what some of you are like out there, wanting to just rip it all down and start again. Throughout Manchester's recent developments, we hope much of its charm stays intact. It still remains a hotspot for period film and television, transporting viewers back in time where the facades tell the story. Its history and character must be enhanced, not erased. These are some of the projects that we've completed as Cornier, and I'd like, to jog your memory. But for a city like Manchester, you must ensure ambition can be met with practical, fit-for-purpose facades. And some of the projects we've supported, the Etihad North Stand extension, Vox, Circle Square, Christie Patterson, which I'll draw a bit more attention to, Embankment, BTR Towers, First Street, which is just around the corner, and Manchester Airport. So the Christie Patterson Research Centre by BPD Architects. This facade design moves beyond appearance. The envelope had to perform technically while supporting architectural intent. The key challenge was not one single movement, it was the combination of multiple movements happening at the same time. This is the building movement report. Every building moves, floors deflect, structures sway, aluminium expands and contracts. And in the UK, last week you can have 30 degrees and this week 15. It's quite a rapid thermal change. But the facade must keep performing through all that movement. We used a unitized curtain wall system with an enhanced movement joint. Each facade unit could connect securely to the next, but still allow controlled movement where the structure required it. Think of it less like a fixed tiled wall and more like engineered armor. Each panel locks into its neighbor, but the joint allows controlled movement without losing protection. And on this project, it was about plus minus 19 mil of movement, which allowed that structure to breathe over time. The facade is protected in layers. It doesn't depend on one line of defense. So you've got your outer rain screen gasket, stack joint air seal, internal air seal, and the movement is absorbed without losing protection. Rather than relying on one seal, the facade uses a layered defense strategy, and if wind-driven rain or pressure reaches the outer zone, there are still further lines of protection behind it, which you can see in red as you work further into the back box of the transom. So the Christie-Patterson shows why facade systems need to be more than just a catalogue of products, and the value is in understanding the project-specific conditions and helping the team, the design team, create a facade that works in the real world. I said I wouldn't take too much of your time, but as Cornier, it's been great to have supported so much of Manchester's skyline, and as Novastruct, we can't wait to support more in the future. So thank you very much and enjoy the rest of your day.
Thank you very much, Andrew. Short and sweet, but Andrew will be about next door to talk about anything that Novastruct are doing, or latterly Cornier, now being Novastruct going forwards. So grab him at lunchtime. Right, next up, we've got SimpsonHaugh talking about form, colour and texture. I'm sorry, I've completely blanked on your name. James Hind, sorry. Apologies, everyone. James Hind. We're in one of SimpsonHaugh's buildings here, so we'll talk about all manner of Manchester. Thank you.
Afternoon, everyone. Right, so yeah, I'm James from SimpsonHaugh. Going to talk about a couple of our buildings, but first, given that we're in Manchester, I just wanted to set a bit more of the broader context, really, because this is our work, really, in this city for the last 30 years, starting with this building where we're in now, and migrating towards what we're going to show you shortly, what I'm going to show you shortly. But at its heart, it's really around density and placemaking, really. So I'm going to talk you through some of the context, particularly around Great Jackson Street, but also the wider Manchester context as well, you know, touching on some of the previous presentations, particularly the Studio Egret West one as well, which kind of brings into this context. We have a density problem in Manchester still. This is from 2019. We were about 60,000 people living in the city core at this point. We've come a long way since 1990. In 1990, when we were first starting out as a practice, this hadn't even been built yet. There were about 500 people living in the city core. It was really empty. And we need people, because cities don't work without people. It's all very well having people coming into work, but unless you have people living in the city core, you just end up with dead places at night time. They're unsafe. We needed to move to a city where we've got a lot more energy, a lot more footfall, a lot more life, and with density comes increased facilities, the tram, better shops, better food and beverage offer, and it's a city we start to see today. This country has a really challenging relationship, I think, in terms of rebalancing cities from London up into the regions, compared to our European counterparts and even sort of further afield. Second cities or even third cities are half the density of the capital. We have a massive imbalance between Manchester or Birmingham and the pull of London. This is a graph from 2019. We moved a long way from this point, really. But you can see that even at 2019, where Manchester had started to move towards 24.5 dwellings per hectare, we were still under the density that London was producing as an overall city. So we had a huge amount to kind of move forward on, which is really kind of underpinning most of our work to date. Now, this is obviously quite old. Now we're about 100,000 people in the city, but the aspiration is really to grow more to 250,000. And at 250,000 people in the city, and this is just within the core, we can really start to hold our own as a global city, which is where we want to belong. So that's the context. Back in the early part of the 20th century, it was a dense city. It was packed all the way around the outer ring. All of the brown area here is houses, really poor quality, back-to-back, tenement living, and it obviously had to change and had to evolve. In the middle was where the warehouses were and the industry. We can map on that outer ring, which is the bull's head of the inner ring road for Manchester. So a lot of where we're seeing development happening now is in this kind of mapping of the ring road around Manchester, the middle of which was all industrial, the outer edge was traditionally residential, but of very poor quality. And this is what it starts to look like today. So that rust belt that we think of it as really kind of defines the city core. It is a walkable city. I know that's got, political overtones, but we think of it as a walkable city. The heart of the city in the middle, which is where the civic centre is, you're only really 15 to 20 minutes walk from any particular edge. And that's important because it means you can start to think of that outer ring road as being the area where all of the residential developments are happening, and this is what is happening. So here we've got Great Jackson Street and the framework that we started about 25 years ago. As we move further around, we've got First Street, we've got Circle Square, we get around to Mayfield. That ring road continues through, it's slightly curtailed off as you go through Great Ancoat Street and then out round through into the edge of Salford, capture Trinity Islands and back around in the circle. So it's a really clear diagram around how we're starting to densify the city without putting things in the middle, but with growing that edge, which is I think an interesting diagram. It's not the only way that it works. When we talk about density, the case studies I'm going to show you today really are Manchester specific. This isn't a one-size-fits-all. We're passionate about density, and we know that density can be achieved through a variety of different typologies. The typologies that we're talking about today are really around how we got Manchester from 500 people to 60,000 people and then to 100,000 people. There'll be other typologies that come on that talk about how we might get to 250,000. As we start to develop further over the next 10 to 20 years. These are the sites that we're going to talk about. So down here is Plot F within Great Jackson Street. Up here is our Port Street development, which is on that ring, still in that edge, not within such a tightly controlled area of regeneration, but still within that diagram. And we think about this as an evolving diagram around how we start to migrate through all of these areas, Piccadilly Station through to First Street, Great Jackson Street, but also crossing through into the middle, into the core. We have starting to get pockets of green space, which Manchester lacked for a long time. Mayfield was the first public park in probably 100 years in the city, if not longer. And we've lacked that green space. But now with the density that's arriving through these places, we can start to think about this as proper placemaking, where people really want to live. This illustrates where we were as a city. The red line here is our Plot F contour development from the Great Jackson Street framework. And it's exactly where all of that back-to-back housing used to be. The edge of the industry happening here along the riverfront, but then outwards from there, just endless housing. But at the start of the 21st century, this is the picture that it looked like. It had been replaced, huge amounts of demolition, obviously, houses that were unfit for habitation, but not being replaced by anything else. So we're left with an area of Manchester that was light industrial at best, surface car park. Our office was just here. You wouldn't really want to walk across that car park after 6 o'clock. It wasn't very safe. And the other thing that happened then was that the area of Hume, which is to the south, the other side of the ring road, became isolated from the city core. So there was no reason for that to become part of the city centre. It was really isolated and locked away, which doesn't help the way in which communities start to interact with the city core. Over the last 20 years, we've been working through a period of boom, I think, in Manchester, bucking the trend probably for most of the country. So it's been a real privilege to be at the forefront of how we've started to rethink certain parts of the city. And this is Great Jackson Street, the master plan. Started off life 10, 15 years ago as something a little bit more modest, has since been rethought a couple of times as the market has evolved and as the product has started to become more sophisticated. And this is the edge of the city that you're all probably familiar with. You can see it on the skyline. And our Plot F buildings are these ones edged in red. So you can see how that kind of density pattern has grown from something that was quite low rise to something that was quite high rise and dense. First phases of our Great Jackson Street master plan were Deansgate Square on the left, followed by Crown Street phase 1 and then Crown Street phase 2 along the left. And this is the picture that you kind of see today, although we've moved on a bit even further with the construction of F1 and F2. Now, just to kind of put this into broader context, when this area is complete, together with Trinity Islands, which is just the other side of the ring road, we're talking about a population of around about 26,000 people that will live here. We're already quite close to where that is. I mean, we've got a few phases left to go, but we're getting close to that. That is the same population broadly, based on the last census, as Wilmslow. But at 100th or 1,000th of the overall area in terms of what we're building here. So, which is right, according to cities, you know, where we should be building dense. So we're at about 2,000 people per hectare in this model, compared to only 20 people per hectare out in Wilmslow. So we think this is a very important part of how we think about the sustainability of cities, looking at sustainability in a broader context, beyond the building envelope. And it's important because without these people, we don't get activities like this happening. This is where people come together en masse for communal activities, both inside and outside. This doesn't happen without a critical number of people. The other thing that brings along as well, and it does take time for this to evolve, is the first primary school in the city for over 60 years. So we can't build schools until we've got a certain critical mass of people that occupy a certain area. They're just not happening. But it is happening now. We've got doctor surgeries, we've got dentists, we've got critical infrastructure to support the densification of our cities. So that's the context against which we started to rethink and design the latest phase of Great Jackson Street Master Plan, which is Plot F. Now, the challenge here, I think, with all of these buildings is around really kind of how we build efficiently, whilst starting to be, you know, whilst trying to be as creative as possible. Our starting point on this was really to think about the challenge of the corner. The challenge of the corner is one that you end up with excess square footage at the corners in here, which typically anyone that works in the sort of BTR environment or kind of mass residential delivery, that's not something that gets charged back necessarily. You don't necessarily get a value on that, but you're paying quite a lot to have that extra square footage, about 20 to 30 square foot, that isn't really needed in terms of the raw model. We started to think about how that could inform the architecture, think about the way in which we could design to the corners, whether we cut that out, or in this instance, whether we start to give some form and some shape to the building. The other interesting thing, and again, this is Manchester specific, is how we deal with the particular ratio of apartments that are required by the city. So 1 beds, 2 beds, 3 beds. It's not a uniform approach, but there are minimum and maximum kind of requirements. So we map that model vertically, effectively, so we could start to think about how we could tailor the floor plate, keeping the central part of it, not just the core, but the kind of the inner ring around the residential components, the same as you go up. Again, a very efficient way of building. But by varying the corner condition, we can actually tailor it exactly to the way in which the brief was starting to work, which is quite interesting. So that's kind of an approach to how we might start to think about the form, particularly dialing back to the title of our presentation. And here you can see we started to think about this as a series of typical plans, but you get a minimum position that pulls the wastes in. You get a typical level that occurs at points up through the building, and then you get a maximum point where there's an opportunity there to actually kind of grow the plan out to the widest point, and that's where we start to introduce the three beds. So the three beds occur at certain points as you go up through the building, that perfectly maps to the optimum way of providing the brief, effectively. So it's very much a plan-driven form, kept to something that's very, very lean and tailored to the brief. This was an evolving master plan. When we were originally looking at this master plan, for this particular area of it, we thought initially we'd have 3 buildings here that would be a little bit smaller. Actually, through an explorative process, we thought 2 buildings would be better, 2 identical pieces that sit either side of a landscape garden. And this was about maximizing that kind of placemaking opportunity rather than occupying building floor plates across all of that site. Positioning both of these 2 either side of the wider plan, responding to the sweep of Great Jackson Street, thinking about these 2 pieces as being kind of 2 parts of a whole, really. And importantly, how they start to work with the wider context. So this isn't a start from scratch piece of land. This is then, by the time we get to it's effectively the 4th or the 5th phase through that master plan, we're dealing with an existing context that is something that has grown up over the last 10 to 15 years. And this is how we started to evolve it. So from a 3-piece part of the jigsaw to a 2-piece part, actually we can create 10% more public space. That's really important. We can actually get 5% more accommodation on there. We've got bigger building separations. And if you add up all the story heights, we can actually reduce the amount of building that we're actually doing. So overall, it's a better solution. In terms of colour, we saw this as an opportunity to really rethink what the pattern and the typologies that we'd already been exploring. This is an opportunity that, not many architects get, where you're re-looking at the same product over a number of kind of iterations, really. And in this instance, we thought, well, actually, the form starts with the corners. The form is generated by the corners. What we want to do is to kind of turn this on its head. The exploration on Deansgate Square particularly was around a unitized curtain wall. All of our buildings in this context have been unitized curtain wall. But it was glass-faced, primarily glass, small amounts of aluminium. Here's an opportunity to turn that on its head, where we've got these flat sides and the open corners, and think about introducing colour, vibrancy into the flat surfaces as an aluminium piece. We thought we might try and introduce a lot of colour, which we did. We ended up settling on a blue and a green. Anodized aluminium from Necce in Italy, which is it's a beautiful finish, very subtle in its colour. We initially started off with something that could be quite bold, but we've naturally kind of fallen back to something that perhaps is a little bit more subtle in its approach. But with the photographs that I'll show you, you still get a variety of different finishes given the lighting conditions. The blue on the left-hand side, the green on the right-hand side, these are our sample panels, metre square, that we looked at in front of Deansgate Square, probably about 5 years ago now, a scorching hot day. And then, with buildings like this, the important considerations are the top, always the top, and always how you hit the ground. We'll come on to how you hit the ground in a couple of slides, but here this is around kind of emphasising again how we play with the corner, particularly, how we celebrate the edges of the building going up, distinguishing between the 2, ways in which we can start to think about the glass replacement early on in the process, always early on through here, working with supply chain very, very early on, thinking about the type of glass replacement, how we could actually make, get the corners to work successfully. What is the optimum angles that we're working with on these corners that allow for both window cleaning, but also from glass replacement when you've got inward-facing facades and also outward-facing facades. Starts to generate a discussion on the width as well. You know, so a huge amount of detail on what the parameters of that corner end up being. And this is a scheme that went in for planning. The key thing for us was these aren't just two standalone pieces. These are things that are actually designed to work with the existing context. So you've got Deansgate Square here that occupy the four buildings in the middle, and then ours were kind of bookending this. And it's about adding something to it, complementing the overall composition, whilst providing something that was perhaps unique in its offer. And we'll all be familiar with this, you know, a series of drawings around how we communicate this, and working with delivery supply chain like Focky. Note to self, the important thing when designing things like this is how you actually then think about blinds and windows that follow gravity and don't necessarily follow the angle of a window, but we solved that problem, and that's for a different talk. And the visual mock-ups when they arrived here on site, this is the dark blue here, and the green. So this is F1 that's following about 6 months behind. This is F2. We thought in this instance, actually, you know, given the challenges of the overheating, I'm running low on time, so I'm going to speed up a bit. Challenges of overheating, we thought we'd start to do something a bit different here, which is explore a glass rapid vent behind the aluminium in this instance, and start to play with the perforations here so that actually it starts to mimic the building as you start to experience it, looking up the building itself. And then the other thing is how you hit the ground. So this, we thought we'd continue that language down, anchor the building with these giant columns, beautiful fair-faced concrete pieces that have been covered up until very recently. And there they are that have just been cast, or when they were just cast. Some photographs under construction. I'm rattling through this now because I want to get onto Port Street as well. But you can see how actually, you know, the important thing for us here was, you know, how this starts to work with the existing context, even though that existing context is relatively new, starting to embrace the shadow and the light play on the corners. And then that beautiful piece of aluminium, when you get different sun conditions hitting it, really starts to take on a life of its own. That was the green one, this is the blue one. And I think some of my favourite photographs recently, now it's certainly the green one has topped out, this is contour, is just how it starts to respond to the Manchester climate. We don't get sunny days that often. When you do, the sun gets picked out, you know, beautifully by the corners, but often it's around how that expresses itself as you go up in terms of the shadow and the light. And these pictures are courtesy of Focky, which starts to show, you know, almost the completed building here and looking across to the west. Similarly, at 1 Port Street, this is further round, if you remember the Bull's Head. This is where it sits. So this is within an area that's called Piccadilly Basin. This is Great Ancoats Street along here. So this is part of the Ring Road, bit that's curtailed, the top of the Bull's Head. And this is kind of the snout of the bull around here. So this is set very much at the top there in number 9. Part of what was the HS2 framework. Obviously that's evolving. We all miss that deeply. And the context here, going back to the beginning of the 20th century, is, you know, this was a fully functioning wharf and basin that was part of the Piccadilly area, linked to the train station, and our site is at the top here. So there's inlets coming in from the basin there, with a wharf to one side. We're pretty much occupying that top left-hand, top corner piece there. And as we've evolved through most part of the 20th century, really, this was an area that fell into complete disrepair. When we picked it up, again, about mid-90s, I think it was, for a series of master plans that we're still kind of working through now, it was surface car park. You can see there's some, you know, a couple of grade 2-star listed assets, one of which is Avro, that Urban Splash finished. And then it's just a sea of car parking, really. And it's not really that long ago when that was still the norm in Manchester. In 2016, we produced a strategic regeneration framework for the city and for our client, who is the majority landowner in that space. They then sold that plot, which was A and B, to our client, Select Property. And at that time, we'd envisaged this plot being 2 separate buildings. This is it from the air. You can see the relationship of what was starting to work through the canal edge, Brownsfield Mill at the top, but very much that kind of patchwork piece of light industrial car parking with some emergence of residential opportunity. This is the physical context. So you've got places like Brownsfield Mill, obviously since been completely redeveloped to what you can see down here. That was Urban Splash. You've got then the historic mills on the other side, form part of Ancoats. Yeah, it's a really well-connected community. And then you've got some of the newer developments here that have formed part of the more recent work. And our starting point here was to rethink, okay, we had gone through the SRF, it was our piece of work in the first instance, but when you then start to interrogate it against a brief that comes in from a different client, you start to uncover different opportunities. Here was an opportunity to reconnect the Great Ancoats Street edge. So this is part of our site here. And the solution there was to actually move the tower back so that we can start to reinvigorate the street edge. And by doing that, that starts to offer up more opportunities to get a connected series of routes through nodal points that start to knit into the wider framework for that area. And this just kind of shows off how we kind of manage those design strategies. So in the end, we're left with a building that is a tower component and then 3 interlinked pieces that start to form part of that kind of stitching together of the city fabric. And gives us an opportunity to think about how we treat the facade in 2 different ways. The tower being something that we knew about in terms of the design would be a unitized piece of unitized curtain wall, very similar to the language that we had been looking at for Great Jackson Street, but an opportunity here to embed that in the area that we're particularly looking at, that red brick mill typology. And here is an opportunity to look at unitized curtain wall that's a very regular array, referencing back that warehouse typology and working with some of the color options. This was a red that we were starting to look at, very keen on how we were going to start to look at using color in the building, bringing that color through to the lower podium pieces that were done in brickwork, using that kind of unitized language, the anodized language in piecemeal parts, thinking about how we could vary the scale and the rhythm of window openings. Just a simple device, whether that is a single window, pair of group windows, or double height kind of window opportunities to respond to different contexts as you go through the building. But at its heart, really keeping a limited palette. And then we move into the inside of the building, an opportunity to open that up with balconies and framing devices around the windows. I am wrapping up. Some visualizations, I think, that show really how successful that is in terms of knitting it in with the Great Ancoats Street edge. And then the sample paneling, where we naturally moved perhaps from a pure red to a kind of a brown and then a dark brown with the visual mock-up. And a really hard visual mock-up with about 8 different subcontractors. The easy bit is the stuff that's done by one subcontractor, which is Focky. The difficult bit is where you've got 8 different people all trying to design their own part of the piece. Interface details, which I don't have enough time to talk to you about. And the sort of the key thing for us was really around the duality of the facade. So we have 2 sides of the facade that have got fins, 2 sides of the facade that are flush. And then you start to see how all those components come together. The richness of the brickwork, knitting back to that warehouse typology, contrasting against the unitized curtain wall. And particularly when you come back to the broader context of the basin itself, how those component parts, we're creating new textures, really, that work within this space. It's not just a recreation of what is there currently, it's an embracing of the color, the form, and the texture to start to create new visual language. And this is how it was finished in February. So this is how it's currently looked. Again, this is courtesy of Focky, some great aerial photographs here. And just to bring us back to a close, here are both Plot F and Port Street together to show the full context across Manchester city centre. Thank you very much.
Thank you very much, James. I think it's quite easy to forget how far Manchester's come in such a relatively short space of time, really, and how central SimpsonHaugh have been to Manchester's sort of evolution over the past 25 years. I mean, it must be a real joy to work within your own context that you've created and helped develop, and have chance and time to reappraise that, I think. But no further ado, I suppose, on to the next presentation. I brought this up because it's a long title, A Data-Driven Framework for Sustainable Facade Design, Methodology and Case Study Validation, presented by Amaldev Premkumar from Ramboll.
Good afternoon all. I'll start with saying something that we fairly agree on quite well, that measuring sustainability in buildings is something quite difficult. And facade is just one part of it, and then we've all been struggling with the same question. So take this quite obvious example that we always come across, which is, what do you choose, a double glazed facade or a triple glazed facade? And when we try to answer that, we are kind of pulled in two directions, because we all know that double glazed facades have lesser material, lesser glass, lesser processing. So it's better in embodied carbon. But on the same side, if you go with the triple glazed facade, then it performs operationally well. So your building ends up spending lesser energy. So in this sort of a scenario, how do you decide between the two? And we all know it's not an easy answer, and the obvious choice is to run both things and then come up with the answer. And this talk is about how we do it in Ramboll and how we have tried different methods and come across a fairly good method which we feel can push us in the right direction. So yeah, so in essence, the question is simple. So you work out the embodied carbon for the facade, you calculate the operational carbon, you put them together and you compare them and you get the answer. But yeah, let's see how that is a really difficult thing to do. So let's start with embodied carbon. So embodied carbon is something that is fairly similar to do because it's a set of sequence of formulas. So you can quite do it well using a spreadsheet approach. So if you have the right structure of spreadsheets, you can start with the material takeoff, the carbon factors, and then you can finally get the embodied carbon. But what we have found spreadsheet approaches lack or struggle is when in a project something new comes along, a different type of a fin or a different type of a precast feature. And that's when these sort of a spreadsheet-based approaches really struggle. So we either cannot, the spreadsheet approach cannot either take it, or we spend too much time tweaking it to fit in, but then end up losing all that time. So in a sense, embodied carbon is a speed problem, is a range problem. You have the speed in first standard approaches, but you lack the range. Now, if you go into operational carbon, it's the other side of the story. It's something really difficult to do. You have to start with a building energy model, and setting that up really takes a lot of time. To do it sufficiently in a very good manner, you have to obviously model the whole building and not a small box model. And to do that, you need to know the form of the building, the wall ratios, the schedules, you name it. And that's just to get it started. And once you simulate it, you need a set of things to do, which is you start with the passive loads, which is actually what you need to keep the building in thermal comfort. Then depending on what systems we choose, we have various system efficiencies. So, and finally, once you have all that, you need to project it into the future. And that's where all these grid emissions and carbon decarbonization comes along. So it, in a sense, on its own is a very complicated process. Now, once we have both of those together, we kind of put it into a graph like this. So here what you're seeing is a base option, which is in the dotted line, and an alternate option, which is in the straight line. So you can see how these pan out over the years. And obviously this graph is difficult to read. So what we typically do is make the base a straight line, something like this, and plot the alternative like this. So in this particular example, what you're seeing is the base option is at DGU, what we talked about, and the alternate option is at TGU. So it obviously has a higher upfront carbon, but TGU, being as it performs better over the years, chips away from that initial upfront, and then by the end of 18 years, you kind of get the payback. But one thing to note here is that at 25 years, you need to replace your IGU. So again, if you had put in a triple glazed unit at the beginning, you need to replace it with a triple glazed unit. So you end up having the carbon shoot up again, and then you finally pay it back at 34 years. So just imagine the facade, the choice we made pays back 34 years later. So yeah. So let's move forward. So the way we tackled this problem at Ramboll, our legacy solution was something like this. So what we essentially had was sets of scripts and databases that was managed by different teams, because this is a problem that requires many teams to come together. So you have the building physics team who does the operational carbon. We have a facade team, and they have the sustainability team doing the carbon factors for embodied carbon. So it was a series of scripts which communicated with each other on demand, and basically did a material takeoff, carbon calculation, operational, and then finally you get the carbon payback. One issue we had with this approach is that the operational bit, although it was automated, was on demand. So every time you want to do a new option, you had to wait for the model to run and come back to us. And that's something which is very difficult to speed up because it takes a lot of time. So we were thinking, how can you solve this issue? And and operational carbon being the bottleneck in this situation, what we did was we used cloud compute. So instead of running one model after the other, we simulated like 1,000 models all at once in parallel cores in the server. So you don't depend on your local machine to run it, you actually run it on cloud. So when you do it, you can do something like this. So this is a real-time iteration of base facade and an alternative facade. And you can see how fast it's calculating the carbon payback. So for each triple glazed unit that is put in the alternative option, you can see in real time what the payback for it will be. And then you can also see in the middle pane how the U values are changing, how the carbon payback is changing, and the net carbon is also changing. So this is what we are at now, which is a cloud-based approach in a way. And to quickly run through the figures that we have seen. So this is a recent project that we did. It's a lab building in Oxford. This is stage 2 again. We compared with the base option to 2,160 options. So basically we had a base facade of triple glaze unit, and we compared almost 2,000 combinations against it to figure out if we can improve, first of all, and if we can improve, which way we can do it. So it included 3 G value steps, 4 options for window to wall ratio, 9 options for U value, 5 options for air tightness, and 4 low carbon steps. So combined all of these, you get a big spreadsheet and a big graph of all the different ways you can do it. And you can see in this quick snapshot how all these various options give you like a various sort of payback period. So it's quite interesting when you have that kind of speed. To make it a bit interesting, I'll quickly run through how this works real time in a way like, imagine that this is a facade, which is a standard unitized curtain wall with double glazed unit. You have a U value of 1, the G value of 0.35. It's standard mid iron, non-recycled aluminum, and air tightness of 5. So this is a typical case, and this is for the Oxford project that I was talking about. The facade area is around 8,000 square meters. The window to wall ratio is kind of fixed. We cannot change that at 40%. The systems we are using are air source heat pumps and electric chillers, and the study period is 50 years. So how can we make this facade better? So obviously the first answer would be to make it a TGU. So let's make it a TGU. So when we make it a TGU, we are also just being mindful that the G value might drop a bit. So the G value dropped 0.5 points. And you can see how the carbon payback is currently doing. So there is actually the payback for this TGU unit. So you can see it's around 23 years, and then it jumps up again, and then it again goes back around 48 years. So this is the situation. So this is good, but now let's assume that to achieve this U value of 0.6, you need quite a thick IGU buildup. And you go back to the design table and you figure out that the standard framing system that you're using cannot fit such a thick glass. So what do you do? So you cannot obviously reduce the thickness of the glass. So the only option you have in that scenario is reducing the cavity. So this is something we all do all the time. So you go from a 16 mm argon-filled cavity to a 14 mm or a 12 mm air-filled cavity. So the U value then jumps up to 0.7. And then you can see that technically this is a TGU, it's a better performing system, but then it never really pays back because the U value jumped up. The U value is quite close to the TGU, but then the additional embodied carbon is so massive that it never really pays back. So how do you, let's keep this and let's move forward. How do you move forward with this? Let's just assume that we can use a low carbon glass. So we are not changing anything. We are using the same TGU, same G value, same everything. The only thing we really flipped was we are using a low carbon glass. And you can see the equation flip instantly. So at year 0, you are net negative. And then it continues all the way through. And if this is the direction going forward, why not? What if we also replace the aluminum? So let's make aluminum a low carbon aluminum. So here we are using a low energy aluminum, like Hydro Reduxa 40. So here you can see how that made the plot even net negative. So it's with the TGU, it's everything the same, but then you see how the equation really flipped. Now, imagine the supply chain comes back and tells you that you cannot use low carbon options, you have to go with standard options. So we took out all of those, kept the glass standard, kept the aluminum standard, but we just made the air tightness a bit tighter. So before it was an air tightness of 5, and then we basically said, okay, let's try to design it for an air tightness of 3. And you can again see it again jumped back. So it kind of consolidated for the lack of low carbon options, but you can see the payback is actually better than when we just used a TGU. So the payback is better. It again shoots up in between during the replacement cycle, but then we are again net negative by the end of 50 years. Now, what if we again make the building a bit more tighter if we are going in that route? Let's make the building a tightness of 2. So now you can see, this is quite interesting because here the payback is at 13 years and it never really crosses the baseline anymore. It's always from 13 years, you can expect the building to be net negative carbon. So this again is a good idea. One thing to also note is we had this assumptions that because it's a TGU, the G value might drop points or 5 points. Now, what if we work through the coatings and find a combination that works with the architect with the visual, everything, and then you can keep the G value at 0.35. So you can see again, this is flipping back. So this is the option that is so far the best we have. And finally, let's go back to the very beginning. Let's assume that we never went this TGU route and we just made the baseline DGU that we had a bit more better. And you can see that's the best option we have. So you never needed a TGU in the first place. If you just went with a TGU, made it 1.0, slightly better double glazed unit, you were actually better in terms of carbon payback. The only thing to note is the net carbon for the TGU might be actually better, or 50 years. But this is a point where I want to note about the grid carbon decarbonization, because if the grid decarbonizes based on the targets, the carbon saved in the future becomes less, valuable than what you can save now. So we might think that at the end of 20 years, our more carbon intensive TGU might pay back, but what if the grid decarbonizes so fast that those savings really don't count anymore? So that's why it's also important to look at the present and then try to design what is only required in a way. So this is the process we really went through. So in our legacy workflow, which was really a Rhino Grasshopper-based workflow, we had complex interdependencies because it was all a software-based approach. We were limited by specialist softwares. And the usability barriers, everyone who has tried to use Grasshopper Rhino-based tool knows that trouble, that it's really difficult to use. And then the main issue are the data sets. Because at the core of all of these are the base data sets that we assume. And to keep up with updating it with every new regulation, every new product, every new update in the market is something really difficult to do. So what we have done is went away from this sort of a Rhino Grasshopper approach to more of a web-based approach, which is easier for everyone to use. Even senior members in the team can easily type in a web page and then you directly come into this sort of a configurator. And of course, you cannot do a presentation at this point without talking about AI. So we are also using AI to update our databases in a way. It has really helped us manage the database in that respect. So so this is the key takeaway that I would like to say for this presentation is that sustainability can be really thought of as an optimization problem. There can be a computational side to it. And like all optimization problems, the more data you have, the more you can simulate and the more you can infer and more you can plot. So it would be nice to think of sustainability that way. It's not about using less, it's about optimizing something. So this is what I want to say in general. So test more. The more we test, some of our intuitions get reinforced, and sometimes our eyes are opened by some strange patterns. So that's my presentation. Thank you.
Thank you very much, Amaldev. And I think you'll be around a bit to catch up if anyone's got any questions on that. Right, last one before lunch, the Hind Dickinson Stadium. So Nick Tyrer and Fabio Moretti from BDP and Arup respectively. What looks quite simple, I suspect has got all manner of secrets that you're going to tell us about.
Oh, that's a bright light. Afternoon, everyone. So myself and Fabio are going to present the story of Hind Dickinson, a few of the big challenges that really drove the development of the project, the envelope as a whole. So the stadium is obviously Everton's new home on the banks of the River Mersey. It's 52,500 seat capacity, and we're primarily going to talk about the brick plinth, the barrel facade, and the big picture windows on either end of the stadium. So Everton have been looking for a new home for the last 20 years. They've outgrown their ancestral home at Goodison Park. They looked for around 50 different sites and eventually settled on this site on the riverfront. You can see it kind of is almost bookends the waterfront. In the background, you can see the Liver building and Tate and Royal Albert Docks in the background. And this site presented lots of challenges that essentially drove the direction that as we developed the project. The first being that the site was a live body of water. It was where boats were mooring up that were bringing in the large ships that were coming down the Mersey. And you can see that fitting a stadium onto this site was relatively challenging. We have a body of water on 3 sides of the stadium, very limited access from the east, and I suppose this presents both kind of an operational challenge in terms of crowd flows and how you get people around this really restricted site, but it also has an impact on construction, lay down space, site offices, the more of the building that you build, the less space you even have on the site. The second challenge is that this dock holds a lot of history, dating back to the Victorian period, quite a few of the bits that were shown earlier in the presentation. And so it was used for all manner of different shipping and coal, and the site is filled with kind of different remnants of that. And what's quite nice is that this is actually, back in Victorian time, was a major workplace for the families of the Evertonians of North Liverpool. But the impact of that history is all over the place on the site. We have the Regent's Road Wall that's listed, the dock walls themselves are listed, the hydraulic engine house that controlled the docks. So all these historic assets were kind of wrapped into the design. They had to be preserved, protected, and regenerated. And the third challenge is that although we're showing these beautiful blue renders, this is actually what the conditions can be in such an exposed position at the mouth of the River Mersey, which again has impacts on operations of the stadium, how we design that, but also you imagine working at height, the risks of just the risks of the program in terms of winding off construction. So collectively, all of these decisions kind of came together we went for a DFMA approach to how we were going to build the stadium, essentially moving as many of those activities off-site as possible, where they can be done in safe conditions, and that reduces the number of people on site, it reduces the number of trades on site, items arriving in just-in-time delivery, so essentially they arrive and get installed, basically, so there's not lots of elements lying around on the site. So the first big step is obviously the dock itself. We had to first scour the dock, in which we discovered 12 unexploded ordnance, which had to be detonated out at sea by the military. The docks were filled with sand from the Irish Sea, pumped in at the same time as water was pumped out, and then this was all compacted. And so essentially creating the working platform for the stadium itself. However, that does lead to kind of a scenario where the ends of the stadium, the north and south, are sat on, let's say, real land, while the middle half of the stadium is sat on the reclaimed dock, which has different amounts of settlement, means we have lots of movement joints and kind of differences between different parts of the stadium, and obviously how that impacts the envelope itself. I think the south section, it's very simple, but I think kind of sums up quite well. You can see at the bottom of the drawing, the 2 dock walls that are maintained. One is actually below the pitch, but hasn't been touched. The building bridges over it. The building touches the south boundary of the site, but at ground level, we've had to really pull the whole mass of the building back, just literally to allow space for people to circulate around the stadium. So all of these kind of decisions are all coming kind of from the site itself. So moving on to the facade itself, the area of Liverpool that's relatively, I suppose, derelict and features all these stunning, big, robust brick warehouses, the Tobacco Warehouse, the Titanic, and particular inspiration was taken from these kind of vertical piers coming up through these buildings. So that represents the kind of the base of the building, the plinth, these vertical brick piers, almost in kind of a randomized barcode pattern that allows us to work with lots of different functions internally and move them around. You will see that some of them are obviously ground bearing, some of them are suspended above the turnstiles, and even the area of the paving that you can kind of see is blue, that's the area that was formerly the dock. So then we have all the scenarios again that on a slightly different portion of the building. The decision was made to get kind of with this DFMA approach that we would use brick-faced concrete panels, again, just to the scale and the ability to install them in a fast manner on that kind of windy site. But working with Historic England, they were keen to maintain kind of a craftsman's touch. And so actually all of the bricks in the building were hand-thrown at a local brickworks. Every brick was cast with 2 good faces that then we could cut in half, and then they would be keyed into the concrete itself. On the kind of, in the background of all this, we do lots of computational design to monitor and kind of keep an eye on all the modules and making sure that we're not making the building more complicated than we need to. There is actually only 4 different widths, and then essentially there's different lengths of panels depending on how we're fixing it onto the building, and that's something that's flexible in the molds that we used. But by rationalizing, it means we can put more effort into making reusable, high-quality molds. However, one bit of that was a bit more effort for us is because of this digitized process where it all was going into a factory to be done, is that we had to individually model all 500,000 bricks, which we did it through through computational design, but it was still, there's a lot of effort going into just modeling individual bricks. This is what that actually looks like in the factory, and so all the bricks are laid at ground level, safely, drawings next to you. We even used augmented reality to be able to scan that. That moves onto the production line where the concrete is poured in with the rebar cage. And this is it's kind of a very safe, efficient way of creating high quality output. All of this then gets stored outside, checked for QA, and then essentially shipped to site, and it was just-in-time delivery. So I think there was never more than 3 of these on site at once, because literally they'd be coming in and then being lifted into position. I think these were a team of 4 people to install, and they just went one by one around the building. And you can kind of see hopefully it's been successful in terms of bedding the building into its surroundings. And on the right, you can see the hydraulic engine house, which obviously was original, but has been entirely restored. And one interesting aspect before I pass on to Fabio is with these panels, because of the kind of dual identity of what they look like, actually inside the building is kind of a very different look and feel compared to the outside. Still robust and very raw, but kind of, I think some people are quite surprised when they arrive on a concourse with the kind of concrete elevation.
Thanks, Nick. So I'm just going to try to dive in a bit more on the technical challenges of the precast panel now. So as Nick just mentioned, these are essentially brick-facing precast concrete element. So they are stacked one on top of the other. And then in between them, as you can see in the picture here, they sit metal cladding, which are supported with that strong back frame structure you see on the left. And so essentially, when it comes to the challenge on this project, I think pretty much everywhere, the challenge of this project has been a movement and how to accommodate the movement, because essentially we had to deal with like quite a flexible structure, quite a flexible foundation, as Nick mentioned before. And the first problem that we had to face when we look at this panel was, can a traditional support strategy manage to provide this level of support and accommodation that we need? So in a traditional way, the precast panel stuck on the ground with at least 2 vertical support, and then they're laterally restrained level by level above. What that caused in our specific case is that there are quite a lot of movement happening, and particularly under the vertical movement of the, let's say, flexible slab, flexible foundation, the precast panel would have like sort of like rotate. And as you can see there, essentially that would have generated an horizontal movement up until plus or minus 66 millimeter, which is really big for facade element. And in particular, when bearing in mind that metal cladding panels sit in between precast units. So this metal cladding panel will get essentially being squeezed and squashed by the movement of the precast panel during service. So the solution that we decided to bring to the table was a bit out of the box. It's a solution that is quite common in civil engineering. Is used under pile of bridges, is used for seismic design. It's really not that common in the facade industry. We pretty much never use these guys here, which are elastomeric bearing. So elastomeric bearing is essentially like a rubber material reinforced with plate inside. And the beauty of this element is that they are really, really good in accommodating movement. So very good in accommodating rotation, deformation in different directions. So what we decided to do was, first of all, to disrupt a bit the traditional way to support precast panel. So we decided to go for a central single support at the base, which is the elastomeric bearing, and then lateral restraint at every level, but then locking in plane the panel at level 2 as well. And the advantage that that brought to the project was that when the structure behind was moving and as way, the precast panel essentially are going to be dragged with that. And the elastomeric bearing at the base can perfectly accommodate the rotation that happened at the point. So that's the beauty of it. And when the vertical movement occurs, the panel can effectively slide vertically without rotating. And they slide again over the elastomeric bearing, and elastomeric bearing again accommodate the rotation that happened at the base. And that essentially results in literally 0 millimeter horizontal movement under vertical movement condition, which essentially enhanced quite a lot the architecture. So effectively, thanks to this, we could minimize joint between metal panel, precast unit, and then of course the overall behavior of the facade got much improved. In the next slide, you can see some practical pictures on how this has been created. So in this one here, you see the elastomeric bearing, which is, probably you can notice a bit lifted from the base with like a grouted bed. And the reason of that is because elastomeric bearing don't really like too much to be submerged in water for a prolonged time. They start to deteriorate, lose performance, they really don't behave very well. So we lift them off from the water line, and then we created an effective drainage around to try to make them perform as better as possible during the service life. In here you can see the lateral restraint at the level 2 and level 3, which provide only out-of-plane support. And this one is the lateral restraint level 2, which provide essentially also the in-lock, in-plane movement. And this one is one of the cases that Nick was mentioning before. So many precast panels don't go all the way down to the ground. They are kind of like stuck on top of a support frame, but the logic doesn't change. So even though they're supported with these big steel billets, the steel billets are sitting on top of like a central elastomeric bearing. So again, allowing this rotation and movement accommodation to happen. Back to you.
Okay, so moving up into the building, we're talking about the barrel roof, which is obviously a much more contemporary geometry, trying to be a bit more dynamic and add a little bit more movement into the design that kind of contrasts with the kind of quite robust base at the bottom. Again, all of this gets set out scripts on our side, and we use this right way through the project. It looks very messy, but I promise that there's a logic that everyone on our team understands. But the main, I think, principle of anything at this scale is really making sure that there's a rational principles that kind of make sure the geometry is set out in a reliable way. So the geometry is set out on, say, pure arcs, basically. We explored lots of different ways of how we can tweak the profiles of the facade to reduce the number of unique panel types. And actually the way, the shape that we settled on was, it was basically a physics-based simulation where you can see on the right, each section of this ladder truss is basically an arc that meets tangentially, but they're all the same length. So actually, the number of panels and the types is all relatively simple. And then we maintain these the scripts all the way through to construction, and it allows us to still step in relatively late and, for example, work out kind of specifics about bracket designs when, say, the structure is faceted, the primary structure, whereas the cladding itself is a different geometry. So we're able to define, say, deviations on bracket sizes. And I suppose it doesn't matter how many stadia you work on, the scale of what we're looking at, it always is a surprise. And so even, you know, when we're looking at these tiny triangles, they are huge and really kind of reinforce the importance of setting up these principles to reduce the amount of complexity and reduce the amount of unique details. These panels, we essentially used a curtain wall jig, and they just lifted into place and hooked in, and they were just able to go one by one. And I think they were installing, I think maybe 15 a day I think there's maybe a time lapse on here, but oh, there you go. So literally just stacked top to bottom and then go, and then within each of those frames is different perforation patterns, kind of adding a subtle texture onto that facade. Okay, and then the final big facade element on the stadium is the picture windows. So on the south and on the north, the south one is, as I showed on the section earlier, is inclined outwards and is facing back to Liverpool, whereas the one on the north is vertical, it's right up against the site boundary, and that one, interestingly enough, offers views out to the sea and a very beautiful sunset, actually, which is quite unusual for a stadium experience. The glazing itself, because we still wanted to encourage as much airflow into the stadium itself for good grass growth, to make sure the grass is healthy as possible, we actually, you can kind of see it on this one, but the glazing is a lapped shingle detail. So there is airflow coming between each layer, but without too much actual wind pressure coming through into the bowl.
Thanks. So yes, again, diving through the technical challenges on the glaze wall. Again, you're going to hear me talking about movement, because that, again, has been the big challenge on this project, as I mentioned before. As Nick mentioned before, I think it's quite interesting to understand, again, the scale of things. So you can probably notice how big and massive the proportion of this facade is compared to human people. You can see those two little guys at the top of the roof compared to the massive facade we need to deal with. So the scale of this project has been really massive. And the complexity and the scale of the structure onto which we are connecting to as well is extremely complicated. So this is the massively complicated structure that forms the primary frame of the stadium, a mix between steelwork, concrete, element connected together, movement joints, really complex. And the glazing wall connects to all of this. So this brittle material, glass, connected to this very flexible structure. So flexible and massive structure, in this case 120 meter long trusses that span from one side to the other side of the stadium. And the facade is connected particularly to a specific purposely built facade truss at the end of the stadium, but again with the same scale that I just mentioned. And the extra complexity is that this massive truss, this facade truss at the end, present a core part at the center that is quite rigid, but then the two wings on the side are oversailing a structural movement joint, so they're quite flexible. And essentially the issue there is that out of plane, the structure moves quite differentially between the core and the wings. So any component that pass through this sort of like jump, they need to resist or accommodate as much as possible this differential movement. And essentially what this can cause in practical terms is warping. So by warping, essentially, we mean when we have like a plane, like a rigid plane, and we try to push one corner of it out of plane respect from the other three. This is possible with flexible material, like metal, way more complicated to achieve with brittle material, like glass, which can break and shatter under significantly induced stress out of plane. So what we decided to do was to provide like a parametric study of this very complex structure. And essentially we plotted all the more than 120 load cases that the structural frame need to resist. And that helped us essentially to identify quite quickly with color coding, as you can see here, like the orange base, the one that presents the highest ranges of movement out of plane, and the one at the point are more critical for accommodation of this movement. And that really, really helped to focus the attention of the entire project team together with the structural team in resolving these particular cases and minimizes this differential movement to avoid inducing warping. And these are some detail on how the panel effectively has been installed. As Nick mentioned before, the panel is staggered or shingled, as you can see in the picture on the left. So there is a bit of a gap between them that helps quite a lot in protecting them from the weather, in the sense that they're kind of like shading each other. But at the same time, it's quite good to, again, mask a bit this differential movement that occur and accommodating them well inside. The panel are unitized curtain wall. They present like a hooking system. The hooks are particularly long, and they fit on top of rods, essentially. And the logic of that is that having like a very long hook facilitate a bit the, again, accommodation of this movement with the curvature of the frame, which is really, really big for the stadium. And this is the end result. So this is no CGI, this is no render, this is no AI generated picture, this is the reality, this is the building being built and in operation in December last year. And you can see that the end result is really impressive, is beautiful, is massive, but beautiful. And of course, crowd populating the stadium already for the season. I particularly like this picture. I think when we were working on the project, we never called the project the Hill Dickinson project or the Everton Stadium. It was called the People's Project. So the focus from the Everton Football Club has always been the people. Let's make like a nice home for our people. And that's the end result. And then here you can see the cladding panel that Nick was talking before. I must say, under quite an unforgiving bright light during the day, and still they look amazing. They look really flat, really, really nice architecture. And again, the contrast with the typical traditional brick of Liverpool. And this is like a very nice view of the stadium from the docks, from the water, with the glass facade, which I just talked about, that reflects on the water. Is it? Thank you very much.
As suspected, a bit more going on behind the scenes there than maybe it looks like at the end as a result. That's us done now for lunch. So the next session starts at 2:35. We'll see you all back there. Go out, get some lunch, get a drink, talk to each other, ask our speakers anything if you can find them. And if the speakers could just stay back for 5 minutes just to pick up some mementos. Thank you very much. Afternoon, everybody. Are we all suitably refreshed? Everyone looks like it. Come back into the room. Right, so afternoon session. Our first speakers are BB7 talking about the Northeast Space Skills and Technology Centre, or NEST, for Northumbria University. So Camille and Ian Gray, not Andrew Spinks. Take the stage.
Thank you very much. Welcome back from lunch. So this is a really good talk to us straight after lunch, I can warn you already. And yes, as was mentioned, unfortunately, Hansen couldn't make it today. So Iain, who worked on the project, stepped in to talk about the project-specific design that we undertook at NEST. So today we'll be talking about NEST as a project, and we'll also look at some background into fire strategy design and how it applies to facade performance. So BB7 has been going for about 16 years. It's a fire and facade consultancy and some other services. We're based all over the UK and Ireland and some presence in mainland Europe as well. And it's really focused on the idea that we should center design around users. And one of the key values of the company is do good, be good.
Yeah, so a part of that, obviously, in terms of the people-centric, do good, be good element is that we are a B Corp. We obviously have been looking for sustainable design for quite a while. Anyone that's heard me rabbit on in previous Zaks may have seen a bit of that before. But we really settled on B Corp as our vehicle for that, because it's really centered around a more holistic approach to sustainability than just follow a process and sort of push out product. It's more about changing how we work. So we're really, really proud that we got B Corp 2024 or 2025, somewhere in between the two. But it's something that we're immensely proud of that we've got, and it really does drive the way that we approach projects. What we're here to talk to you about, and hopefully not try and put you to sleep on, is the Northeast Space Skills and Technology Centre. I did cheat, it's written down there. Or NEST, as it's also known. So this is a development in the heart of Newcastle, part of Northumbria University, and it's partial redevelopment of the Wyn Jones building to create a brand new 7-storey labs and teaching space for the university. It was a £50 million project funded by a combination of Northumbria University as well as the UK Space Agency and Lockheed Martin. And as you can see, it is a beautiful unisized curtain wall produced by Hanson Group. Other members of the design team were Ryder Architecture, SRM, who very kindly produced quite a lot of gave us quite a few images from site to help us out with this presentation, much appreciated. Fire engineer for the project was Centurion Fire Safety, which is where it falls into a bit of a weird character sort of category when you're looking at it. And you're saying, well, why are you here, BB7, when there's a fire engineer on the job? And that's because we were working directly for Hanson Group, providing them with specialist fire and facade engineering sort of design input and capacity in order to make sure that they were delivering a compliant design that could go to building control and ultimately met the functional requirements of the building regulations. So why is NEST a useful case study in this condition, other than the fact that we're really proud of it? It is a complex facade. It's worth noting that when we spoke to Hanson before this presentation, we sat down with Andy Woods, their MD, and basically he said, that was the most complicated unitized job I have ever made in my life. Not one single panel was the same, which kind of defeats the object of what you would imagine unitized to be. What that does mean is that it was great fun to engineer from a fire engineering perspective and a facade engineering perspective, and it was a really interesting job for us to get involved in. A lot of complex details, lots of things that we could get involved in. Multi-party coordination, it's not just turn up, do your job. It involved a lot of collaboration, a lot of working together alongside the rest of the design team, SRM and their sort of like really strong technical knowledge on facades, alongside Hanson, their supply chain, the fire engineer, everyone working together really to bring this together. Evidence-led process. You would like to think with a space technology building there would be a science-based approach, and there was. It's part of proving to building control that we've got a robust design is making sure that that is backed up by tests, by engineering, by how we have approached this. And finally, it's great to show a real industry lesson. This job is basically done, and it's been successfully delivered. So it's great to show how we've gone from start to finish and how we've achieved that.
Brilliant. So before we go into the details of the project, we'll do some review of fire strategy, how they interact with facade design, and some of the performance requirements that should be defined in the fire strategy. So I don't know how many people are aware of these documents. So it's a suite of research documents that were written in the late 40s, early 50s, called post-war building studies. And you can trace the building, part B of the building regulations and ADB in particular to these documents. So it talks about life safety, it talks about protection, structural integrity, etc. However, when the post-war building studies were written, buildings looked like this. They had a lot fewer insulation material. There was not really any combustible materials within the buildings. So we're applying rules and guidance that were developed in the 50s to buildings that look like this, which clearly is a big step away from the principles that the building regs are based on. So it's worth noting that you really should look at the facade as part of the whole fire strategy, and it needs to be considered carefully by the fire engineer and then implemented properly on site. There's a lot of regulation that talk about facades that relate to fire. So ADB we know about, but there's a lot of different ones. If you're looking at curtain walling, most likely you're immediately into a fire engineered solution, so British standard kind of approach, or deviating from ADB or from BS 9999 and 9991. And it's worth bearing in mind, these are only about life safety. So if you have any project that talks about loss prevention standards, it's a different kettle of fish altogether. But fire strategies should be coordinated with the facade. So the materials and the design and the compartmentation that you choose will change whether you have sprinklers, corridor length, location of staircases, alarm systems. It's really a holistic approach to building design. Saying that, we'll talk a little bit about the elements of facade that get specified within a fire strategy. And these can be very hard to find in a fire strategy. So if you can't find them or if they're not clear, please ask your fire consultant for clarification on this topic. First one is reaction to fire. So it's to do with the way that materials burn. So do they burn? Do they char? Do they drip? Do they smoke? If you want an interesting read and you haven't, BR135 is a good document to go and read up on that topic. And it introduces the idea of rapid versus restricted spread of flame, which a lot of other guidance is based on, like PAS 9980. And it's the idea that if you have a facade, the rate at which the fire spreads over the facade should be limited and based on how fast people can evacuate or how fast a fire can be put out. So it's related to evacuation strategy and sprinklers, etc. We do have to use materials that have some level of combustibility in facades. You can't have just A1 rated or A2S1D0 rated materials, unfortunately, but you have to use them carefully and consider where they've been applied.
So what that means in terms of Nest, in terms of how we then approach this, and we will go into this in more detail in further slides, but it just meant that when we were looking at the materiality, and again, when we were engaging with Hanson and their supply chain, we're looking at what can they physically get, what are the combustibility characteristics of those products in context of the wider fire strategy and the risk profiles within the internal environment.
A second aspect that we consider is resistance to fire. So it's this REI idea that you see on some documents, which has to do with structural integrity, fire integrity, and insulation of walls. This is not normally achieved by the facade, and on Nest, the curtain wall was not achieving that function. It was done by internal linings, which is fairly common. So your SFS or your block work would achieve your resistance to fire where required. It's worth, though, checking that that's what the fire engineer has assumed on your project, and they're not expecting your facade to achieve that function. So same, a coordination item to be discussed as part of the design process. And finally, and I think the hottest topic today, because this is really challenging in curtain walling, is compartmentation. So if you go to ADB or BS9999, the diagram looks like this. That does not look like Nest. It also doesn't look like any of the curtain wall jobs I've worked on. You've got this idea of two leaves of external walls and fire stopping and cavity barrier. It's very hard to relate this to a curtain wall project. So you start having to immediately engineer a solution which is not strictly linked to this guidance document. For curtain wall, it's particularly difficult because you start looking at different product by different manufacturers. Do you rely on multiple test reports to be able to evidence the performance of your curtain wall? And I'll point out this is not a photo from Nest. This is from a fire risk assessment of external wall. Unfortunately, curtain walls and curtain wall compartmentation is very difficult to achieve. So when we open up curtain walls that have been there for 5 to 10 years, this is the kind of details that we find. So compartmentation is not achieved. You've got voids everywhere. Maybe the bats have fallen through because they weren't connected correctly. You've got concealed voids that nobody's considered. It needs to be coordinated prior to going to sites. If your access is poor, if you've got brackets clashing with your fire stopping or with your cavity barriers, you won't be able to achieve a robust design. So when designing curtain walling, in particular for compartmentation, what do we look at? So, sorry, I realized, where's my slide? Yes, sorry, I've realized I've missed the top bit first before we go on. So there's 3 mechanisms of fire spread in curtain walling. Leapfrog, which means that you go from one glazed element to another, bypassing the compartmentation at the slab edge. There's no huge amount you can do about that unless you're introducing fire-rated elements. We tend not to design for this unless, as I said, it's required from the fire strategy. Failure of fire stop compartmentation is the other aspect. So you design your fire stopping separately from your curtain walling, and then fire spread within the curtain wall. So either within the frame, within the spandrel elements, or within external cavities, such as rain screen on the outside. So these are the kind of details that we end up looking at. For fire stopping in particular, we still look at different test reports. So we do look at 1366-4 and 1364-4. Our fire team have reviewed both, and they believe that you get different data from both, and it's worth looking at both together rather than relying on the newer standard only. There's other explanations, but the methodology of how it's tested, where quite often it's fireboarded on the inside, means that it's worth looking at both. Typically, when you're designing fire stopping, you do look at test data, you look at bracket interfaces, you're trying to avoid the brackets penetrating through the fire stop or reduce it as much as you can. It needs to be mechanically fixed, obviously. It cannot be penetrated by aluminium framing unless it's been tested that way, and very few products are tested with aluminium penetrations. And curtain wall bracketry should be protected, because if your facade starts falling away from your structure under fire, you've got voids that create, and immediately your fire stopping has failed. And then the second aspect, which is to do with compartmentation in curtain walling itself, is looking at all the voids that we know exist. Fire engineers sometimes need a little bit of help on that one. So extrusions, spandrel panels, and our approach as BB7 is typically require 150 mil fill within large extrusions in line with the fire stopping, and then review each of the other cavities on the project by project basis. Obviously, if you've got sprinklers, if you've got bulkhead, it becomes a very different design, and other considerations come into play. So summary, this is always a fire engineered approach. You cannot directly link it to BS 9991, ADB, or any of the other specialist guidance. You can't just get a test report from a manufacturer and call it a day. It does need some level of fire engineering review before you can justify that the design is sufficient. And there's other things that you should be considering. So residential high-rise is a very different project to design for than a educational building. And typically, you would want to close voids within the assembly, in particular at the slab level, to prevent heat and smoke traveling through your assembly. Cool.
Okay, so we'll go into a bit more detail now on what this means, having set the scene for Nest and how we approached it. So if we just skip to the next slide, you'll see here that some bits are linear, some bits we can run in parallel, but essentially what it boils down to is to starting with the original intent from Ryder and some initial details from Hansen on how they think they can build it alongside the fire engineer strategy, before then weaving our way through what our bank of test data that we have available to us and starting to iterate the design. And as you can see, that's quite a winding road to get to a final solution. Before with a couple of fire strategy coordination sessions thrown in there as well when we're speaking to Centurion and going, what do you feel comfortable with from this perspective? And it's very much a two-way street on that side. So as I mentioned, it's going straight through the fire strategy review. And what we do is we take that fire strategy, and from that, we then develop a fire strategy review document. And that highlights all the RFIs that we would need Centurion to answer. And a lot of that refers to things like, how are you venting smoke at the building? How are you approaching fire stopping? What is your sprinkler system? And how long is it going to run for? All of these things form key decision points that we can make in terms of sciencing the solution. We then go into the drawing reviews almost in parallel before we issue that fire strategy review. So it becomes a comprehensive set of RFIs that also went to Hansen's team and Hansen's supply chain to start bringing together elements such as combustibility of things like packing and spacers, thermal breaks, which the amount of times I've had conversations about thermal breaks being exempt, but it's not a residential building, so therefore how do you approach it? It's a long and iterative process, and it's very easy to fall into the residential mindset. The design note, which I mentioned just, is sort of the culmination of all of that, before we then move on to a series of iterations, slowly eliminating the RFIs and the questions until we get to a coordinated response that covers all of the different interfaces, before finally sort of culminating in a singular document, with the aim of that going to building control, or if this was a residential building, the BSR, but in this case it was building control. It took a number of revisions, 5 revisions to get there, but we got there. Key things that we dealt with and looked at. So, as Camille mentioned earlier, the slab edge and perimeter fire stopping, key, critical, and is the major thing that we need to deal with, and is not supremely well covered in test data unless you test every single solution in every single manner. So that was, as mentioned, a combination of the 1366-4 and the 1364-4 tests, which is, if anyone doesn't know, it's the spandrel panel built into a rig, and then you burn that, or just the linear gap seal between 2 leaves of concrete. You need data from both in order to get an engineered solution out of that. We looked at the residual cavities in between panels. There was the spandrel panel had a ventilation gap within it that ran across a slab level. Key to figure out how we're dealing with that and how we're addressing that. Again, there is a slide a little bit further on that will show that. Column interfaces, columns were intermittently painted, but in some cases were quite close to walls. How do you deal with that? That actually formed part of our scope. It was kind of a late addition, but it was something that we looked at. Bay study geometries, how are we interfacing all of the different bays? As we mentioned, it's a complex job. There's a lot of different arrangements. No one panel was basically the same. So it was a lot of looking at how can we rationalize the approach. And as mentioned before, material performance, looking at how we're dealing with things like reaction to fire as a key element, and what can we reasonably exempt, and what do we really need data for. So a bit more on the evidence and testing, very briefly. So we're very lucky because we work for a fire engineer. We've got a lot of data, which is lovely. And we've got some NDAs with some fire-stopping producers, as well as Hansen's own suite of data that they have. In this condition, we actually did a lot of work with Hilti. It was Hilti's Firestop that was the product that was being used, and we did a lot of back and forth with them on the content of their ETA and the backing behind what goes into that ETA. Unfortunately, as ever, you pick some holes, you find where the gaps are, because that's your job. We have to make sure that this is solid and robust. But that's where our fire engineered solution of other banks of data came into place. And that meant that we could make sure that we were protecting the aluminium elements where they needed to be protected. We could consider the sprinkler systems. We could look at introducing more dense rock wool in order to shore up some of the details. So the Hilti system is based on a 60 kilograms per meter cubed density. We could up it to 80 and then use other data to prove that worked. So that is a part of the solution, as well as fixing details, using other guidance, bringing that all together. And this is some of the details that we're looking at. So this first one here, this is what I was mentioning before. This is the Firestop detail. We were also looking at amounts of penetration and how much that's backed by previous data in terms of stainless steel, in terms of bracketry. We looked critically at fire escape routes and provided sort of higher level performance in those areas. So we've got a side rise 120. The ASFP gives a guidance that essentially says you shouldn't mix fire protection producers. You shouldn't be using side rise with Hilti, for example, unless you're looking at a fire engineered solution. And that is key. That's the key element that we could bring to Hansen's development. Also, where that interface comes with vertical barriers, you've got internal cavities within the curtain wall. How do you deal with those? How do you stop a route for hot gases and smoke and flame to get through and past that vertical fire stop? So again, details like that. Three-dimensional images as well to make sure that it's clear and understood as part of the fabrication and install. Identifying spaces, identifying cavities, identifying materials, even down to isolation tape. How do you justify isolation tape? It's theoretically combustible, but were someone to question it, do you have a reasonable argument against it? That's the sort of thing we're looking at. And listing these all down in a combustibility schedule, making sure that it's abundantly clear so that when someone's looking at it, they can see that we've considered everything. Cavities, that blue line there represents the cavity that was running past the fire stop. There's a really good test that was done in the 80s that essentially used a variable cavity width to prove whether or not the chimney effect happened and established a critical dimension of 25 millimeters. At 25 millimeters or less, the chimney effect doesn't happen because it chokes airflow and can't let it progress through. It's a fantastic test report and is a really good basis for justifying more fire engineered solutions alongside where you are anticipating the heat and smoke and flame to get. We also looked at internal wall compartmentation. We actually ended up having to specify thicker plasterboard. We ended up with 3 layers instead of 2 in order to prove a robust detail because there was a larger cantilever on the plasterboard. It was delightful and awkward and wasn't particularly popular when it came to putting extra plasterboard in, but we got there. And also AOVs, just in terms of making sure that we have enough square meterage that is deploying in the right way. It's providing what the fire strategy needs. And we end up with this, which looks cracking, I have to say. Very biased, but yeah, it's a great looking project, and I have to say I think it's one really for us to be proud of, and Hansen and everyone in the team.
Brilliant. So going back over the lessons learned from this project and the work we've been doing with fire engineering of curtain walling, you need to start with a fire strategy. I will say even further, you need to start by talking to your fire engineer. And historically, fire engineers were not appointed for implementation of fire strategies. That is changing. There's been guidance coming from the IFE and senior leadership in a whole load of different consultancies. So they should be coming up to speed and be given scope to support the facade industry on that topic if they're not asked a question. They should be. Design interfaces, as we know with weather tightness, interfaces is where facade fail. That's also true for fire. So if you've had to think about it from a air tightness or water point of view, it probably has a fire issue that you need to look at. Use test evidence appropriately. So don't just rely on test evidence. We know that you have to interrogate test evidence, make it relevant to your project, and expand on it through engineering if required. Coordinate early. If you're on site and you're having fire engineering issues, it's a bit too late to try and resolve them. And badly coordinated design means that a fire stopping cannot be fitted. You will end up with legacy issues. So do it before you go to site. It's better. And like everything in facade, make it inspectable and buildable and maintainable, really. So you've got a chance of maintaining the fire performance of your facade in the future. And most importantly, this is an iterative process, so it will take a little while to find a solution that's cost-effective, that's life safety critical, that meets the functional requirements of the building regs, and that can be built. Thank you.
Thank you very much, Iain and Camille. I think that was a fantastic advert for fire engineers talking to facade engineers there. I think that's why you should talk more and do it as one service. Right, and following on a similar theme, compliance, Craig and Sean talking about Gateway 2 and Gateway 3 from SimpsonHaugh. Take the stage.
Thank you. Good afternoon, everybody. Not sure if there's a moan or a groan. This isn't BSR bashing. This is some real life examples and sharing some insights as well. So some of it you'll no doubt be familiar with, but if there's a couple of nuggets in there, then it's well worth listening to. Who am I? I'm Sean Robinson, Director and Head of Building Safety at SimpsonHaugh. Got my colleague Craig hiding behind. Craig is our Building Regs Technical Lead and also our BRPD guru. Bit of an interesting fact about Craig as well. He used to be a reg lead for the BSR, Gateway 2, Gateway 3. So brought a wealth of knowledge, of experience into our business, some of which we will touch on today. I've mentioned some of it is our own experience. Excuse me. Some of it is also courtesy of the BSR, albeit we've paraphrased as we go through. You may be familiar with SimpsonHaugh, you may not. Consultancy practice, our in-house fire engineering team, fire safety, building safety, rights of light, party wall, project cost management, so the whole shebang. So what are we going to be talking about? I kind of touched on it already, really. An overview, key lessons learned from Gateway 2 submissions, causes of delay, how to avoid them, common pitfalls. What is the BSR really looking for in compliant applications? And best practice approaches to overcome and strategies for embedding compliance as well. So this is something that happened fairly recently. We were asked by a client very last minute to attend a BSR meeting to support them, to try to sort of decipher and determine what the issues were around rejection. What we found was that the BSR is considerably hardening its stance, both on RFI query numbers and timescales for remediation applications. So we've heard a lot today about new build and innovation. This is very much focused on existing high-rise buildings and where the pressure points are. So BSR spoke plainly about reducing the allowable number of RFI questions, stroke items, before a rejection occurs. So not the number of RFIs per se, but the number of questions raised. They were looking to reduce that down to 20. Previously, that was sort of around about 30, 35. Their RFI response times as well, reducing to 5 days. Just take a moment to think about that, five days. Pretty tough, and then that gives you time, supposedly, to respond, allowing 2 days response time for any follow-on RFIs from the first response. So really, really challenging, and you can see where this is potentially going. What does it do? Well, It reinforces the need to have a clear, well laid out application. Provide all your necessary relevant regulations, Schedule 1 requirements, remove those outstanding design queries. I think what you also need to consider, especially with this one, was this was a facade application. It was rejected. They didn't think to include sufficient detail around cladding fixings, substrate and substantiated bearing, wind load justification and calculations. Just overlooked or not in as much detail. Clearly, the hierarchy of RFIs was, believe it or not, structure, fire, and then thermal. The rest follow. The problem stems where you've got an MDT being put together, and it could well be that the RBI is joining that MDT 6-8 weeks down the line. So already the clock is well and truly ticking and leaves you falling short somewhat. So for us, to kind of determine that direction of travel through that assessment, albeit coming in late, it was very clear and obvious that ultimately they were only ever going to reject it. Key reasons that cause delay or rejection. So I've kind of broken it down into 4 key points, and I'll follow on in terms of what that looks like as we go through. So poorly organised documents. So the BSR's assessment relies on your documentation first and foremost. They are coming in cold, okay? So to progress those applications, they need the right level of information, the right documents in the right order. So to overcome that, what is it that you need to do? You need to set out clearly what that project is. Sounds simple. What building regulations it needs to comply with, how it will comply, and how you are going to evidence compliance. Think about using 3Ds, photos of the building work, red lines, annotate, draw the BSR to that information. Use a clear portal folder structure to break your application down into clearly labelled parts. Use a clear index to signpost. So 2 of the sort of most important documents, your building regs compliance statement and your fire and emergency file, they will interlink. You will be referencing them throughout the Gateway 2 application. So ensure that they talk to one another and are easily led, or the BSR is easily led to them. Make sure that all your documents include relevant information and relate to the correct building, believe it or not. Some of what we've seen doesn't always relate to the building in question. Remove any comments as well. That's often something that's overlooked. So think about good practice, organising your documents, and it will enable the BSR to make sense of your application. And again, bear in mind, they are coming in cold. So the more you can do to guide them, to steer them, the more that they will be reassured and have confidence in your submission. Incomplete design information. So before they can proceed with any decision making, they need to be assured of the design's maturity. So applications should be finalised, confirm design, systems and interfaces, and clearly noting that your Gateway 2, in essence, is the equivalent of REBA Stage 4. That's where it stops. Anything REBA Stage 5, 6, 7 is on to Gateway 3, unless you are talking approval with requirements or staged applications. The procurement process, you need to think about the parameters of what materials you're going to be using. Is it available? What's the lead-in? Is that going to cause problems? And Craig will touch on strategies to maybe compensate for that further down. Given the timescales associated with the remediation work, it's unlikely that deferring elements of the design will be appropriate. So any proposed requirements needs to be substantiated, really fundamental to the design. Without that, expect a rejection. Statements of future intent, such as design details, will come later when the subcontractor has been onboarded or testing will be undertaken during construction. It won't wash, I'm afraid. It's likely to undermine a successful application. Another thing that we've seen anecdotally is subcontractors, the supply chain, not being engaged early enough and actually not paying them is not an excuse. The BSR will simply not accept it. Okay, unsupported, non-worsening claims. So where you indicate that your proposal will not reduce standards, supporting evidence must clearly be provided. And any non-worsening arguments must include a comparative analysis that clearly demonstrates all regulatory requirements will continue to be met. There's a couple of stats there on the presentation. I won't go into them, but it gives you a feel, albeit they're from 2025, but it gives you a feel of the direction of travel and what they're struggling to overcome. I'm not saying that we're not BSR bashing here. We're trying to work with them. We're trying to collaborate. We are seeing improvements, but the simple things around an application make a big difference to overcoming some of those hurdles. I will pass you on to Craig. Thank you.
Thank you, Sean. Good afternoon, everybody. Just continuing the theme from the examples given by the BSR, these are common technical issues, things that continually come back for lots of applications, reoccurring issues. And I'm glad with the first item that we had BB7 to give good practice. But the examples that we've received from the BSR is that fundamental aspects of fire performance, the design, fire-related specifications are not provided, even on the most basic level. For example, the fire performance of membranes, even the cladding panels themselves are not declared, specified, let alone the hard technical standards behind that, the field of application. So they're hitting a stumbling block straight away. A second one is lack of structural loading calculations. And again, speaking to the MDT structural engineer, this is very basic stuff. Things that a structural engineer is expecting to see from the design team to substantiate the wind loading is okay. The structural support to the cladding is provided back to the building, and the existing building, in these cases, can take the load, either the substrate and the frame behind. And then a third aspect is, again, this is cladding, simple stuff, but insufficient explanation or evidence for cavity ventilation. I myself have seen a submission where the cladding rails have closed off the vented cavity. The engineers didn't see it, and the architect, the designer didn't see it, but it's a fundamental issue that there's no ventilation to that rain screen. And then again, simple things, U-value calcs, interstitial calcs, substantiating why, and the specifications of those materials tied into the fire performance. They were lacking. So I just want to say a thank you to my ex-colleagues. I thought before I forget, so thank you to my ex-colleague, Jane Carroll, Head of Cladding Remediation, and also Carrie Ann Griffiths, my principal, for providing information and also information on this last slide. I think it's really good to see there's a change in, shall I say, perspective and direction from the BSR helping industry. So one of the items that I've said in collaboration with the CLC is developing guidance on fire engineering. So fire emergency file, and also the building regulations compliance statement. As Sean's alluded to, these are really the two key documents. I've got to say, as a designer myself, the building regulations compliance statement is one of the most critical documents. It provides, well, how do you comply with the design from start to finish a design process and the evidence. Schedule 1 of the HRB regulations, it's the least amount of information provided. I think it's 2 short paragraphs. So it's great to see that information coming through. The other thing as well is that BSR is going to prioritize collaboration, clear communication, and faster progress, but without compromising safety. The way I read it is greater engagement with the applicant, with the design team. So arranging those meetings with the MDT and the designers. If nothing else, I've seen my own perspective is the difference of opinion of the questions being asked in RFIs. Before you can even answer the question, it's understanding what the question is. I think that really helps. And if nothing else, this is where we are on these applications. We're on hold at the moment because of this reason. So at least you don't go into this black hole. So moving on is, for example, consistency of approach. And I keep on looking at this slide for the days I've been reviewing this presentation. And I do look at it and say, don't we all do this? Don't we all understand this as a given? But I have to say, from what Sean's raised previously, from my own experience and what the BSR has said, is that these are missing. So for me, it's say what you're going to do and do what you're going to say, particularly in the building regulations compliance statement. So I'm thinking of cladding remediation. You've got the FRAW over here saying there's a problem. You've identified the scope of works. That engages which bit of the building regs you need to comply with. Then you're going through your design rationale. For example, BBA's been discussing it. BB7, been discussing this, and the process to go through there right to the very end of the evidence. The BSR is always looking for evidence. So, and also state assumptions and how these will be resolved to ensure compliance. There are things that you might not be able to do. Going back to that substrate, you suspect it's this, there are some drawings. You've done some survey. You're expecting to see this, but it's an assumption. To close it out, we'll go on site, open up, issue a report. If there's anything strange, we might be in change control, but we've covered the bases. So avoiding gaps in the submission. For example, we've talked about missing calculations. There's lots of different things they're expecting. I even saw a report the other day, speaking to the BSR in an RFI meeting. There was a desktop study. This is an existing building, it's been there for 40 years, but the desktop study said a further report may be required, a recommendation. And that might just be a coverall. BSR immediately raised it and said, where's the secondary, where's this review? It hasn't occurred. Even if it's just a statement by the structural engineer or whoever, we've reviewed this, we don't consider it necessary. You've got to close these gaps. And avoid clashes between documents. Some of it is really simple. There's a reference that doesn't link. There's a clash between one document, for example, the building regulations compliance statement, file emergency file. Or I've seen specific examples of projects, another application is actually the documents are used. They haven't even changed the names. You do start to think, what's the quality of this submission before you get into the nitty-gritty detail. So I'm really saying reinforce your application rather than dismantle it. Build it up, that piece by piece. And I see it as a sliding scale. This is the scope of works. You're building up to all this evidence. And this is only at Gateway 2. So moving on towards, and I have to say this slide should really be how to avoid change control. Change control is there for a good reason, but for an existing buildings, we know it's going to be different. So survey as much as you can, find out what you can, but it's going to be wavy, it's not going to be straight, it's going to undulate. So how do you allow for that? Because I know as a designer, when I've not been doing BSR work or anything else, is that you go through that flow of all the information you're accruing from different sides, you come to a really good conclusion, it takes a matter of time. If there's an ad hoc change, during construction, you're not thinking that way, and you're very easy to miss something that you would have interlinked potentially 6 months ago. So ways of avoiding this, or actually just making life on site easier, is allow for tolerance at design stage. Don't forget, change in dimension could be a change control, for example, corridor widths. So if you know the building is out of tolerance, determine what the tolerance is. Your details, your facade drawings are not saying 50 mil, for example, that cavity, or 38 mil, it's saying 70 or 30. And you've designed, for example, the cavity barriers to allow for that, it's in the field of application. Your cladding rails allow for that tolerance. And for me, what's really important, the contractors have seen this. They're not just saying, we never hit 50, it'll never be achievable. They've determined, they've looked at it, going, there's a range, I can do that. But if it's outside that range, the contractor should duly flag up as a concern. Then you might have to go into change control or just review what's happened. Some other option is another way is providing options. Now, this is good for example, pull-out tests. Keeps on coming up repeatedly in terms of how to resolve this with the BSR. So what happens if you're on site, you've gone through Gateway 2, it's all validated, design's great, pull-out test fails. What's the solution? Because straight away you're changing the fixings, you're into major change. So why don't you have the alternative solution for that pullout? So we tried it, it failed. We tested with the alternative solution that we gave to the BSR at Gateway 2. it works. So you interchange control just to identifying you're doing something slightly different, but it's already covered. You're just recording where you've used different fixings. But what that is really the next part is get around the table. You've got these contractors with lots of experience. Designers tend to look at the model or the drawings online, get together, share that experience. These are the problems that go on site. It will not be straight. So how do we design for that? All right, moving on, and this is a short presentation, is accompanying documents moving towards the submissions. Now, I've got to say, as a reg lead, have you answered the question? I, as a reg lead, would be looking at this. We've got the RBI, fire safety engineer, all the other team, facade engineer, looking at the actual details, the design, but these are procedural requirements that I need to be satisfied that you've covered. So the big thing I find is straight away, as soon as I got the documents, PDF, I'm looking at the number of pages. Is it appropriate? Is it too short? I've seen documents 300 pages long, includes a kitchen sink, a photo of a kitchen sink in a brochure, and it's muddled. So really I'm saying signpost how you've answered those questions in Schedule 1. So effectively, it avoids me doing a keyword search because I'm really trying to say, yes, this is okay. But I'm getting into a keyword search before I've even looked at the quality of the submission because I can't find where your answer is. So the building regulations compliance statement and the fire emergency file, two most important documents. These are the ones the RBI and the fire safety engineer looks at. I just like to run out of time. But I've got to say, for existing buildings, I think it's really important. The fire emergency file is based on existing building. There are two factors within the fire emergency file. How your building work, not CDM, affects the existing management of that building, and how the fire brigade, if an emergency, needs to access and put the fire out. So your scaffold, are you closing off your AOVs? Are you putting your laydown area in front of the dry riser intake? Where do these things go? And then after you've built it, are there any subsequent changes onto the management of how that building is run? So you might have changed some facade, there might be some different elements, even the maintenance. And then moving on to the construction control plan, it should say, is you're really starting to say, right, how am I going to look after the site? How am I going to record this? It moves you towards Gateway 3, but you do it at Gateway 2. Really think about how you're going to record all this. So in conclusion, and I'm please wrapping up soon, is that I have to say it's a back to basics approach. I've been in meetings with the MDT, structural engineer, start to have an argument with the design structural engineer. The design structural engineer thinks the MDT structural engineer's got no clue. I have to take him to the side politely and say, dial it down, take out the personalities, be really factual. Be simple in the explanations, back to basics. This is why we've done it. This is our rationale. We are substantiating it. Sometimes just to convince the RBI that you're doing a good job, because the RBI is one of the most important people making the decision, determination. Structure your submission so others can quickly understand it and find evidence. I have to say, virtually all the reg leads that I ever met have got no building experience. Some of them from pensions, Department for Pensions. There are legal people there. They don't know building. So part of that is convincing them that you've done a great application. Keep information clear and logical. Focus on relevant requirements. This is your questions in terms of building regulations compliance. Encourage open collaboration, challenge, and determine what's the best practice. And that's not really rosy tinted. It's sitting down with the people, challenging them, but doing it proactively and constructively across the designers and contractors. Work together. So, and it is an examination. I've got to say that no matter what. We are examining what you're doing, and we might not have that discussion beforehand. They've already started to form an opinion before they might meet. And lastly, I've got to say, Gateway 3 is really focusing on what was built. Gateway 2, brilliant, you've proved it. The design is compliant. Gateway 3 is all about justifying what was built, then complies. You could have a completely different design. You're going to have to prove that it complies. And then really it's all of the things, your inspections, your reports, your commissioning, photos, illustrate that. And to me, extend the building regulations compliance statement. You've got your design. This is how we achieve part A. This is how we achieve part B. These are our evidence. This is the cross-referencing. And at that point, I've got to stop. I'm passing to Sean.
I think
Thank
we're
you
being
very
kicked
much.
off stage. Hope you've enjoyed that. Thank you for listening. We'll be around for Q&A afterwards if anyone wants to speak to us. Thank you.
Thank you.
Thank you, Sean and Craig. I suspect there's a lot more to say on that subject, and you can grab them both later. I think telling around about clarity and concise submissions. Right, next up we've got Andrew Pries from Boston Valley Terracotta talking about high quality sustainable facades and how terracotta does that for us.
Hi everyone, thanks for having me here today. I'm here to talk about how an ancient timeless material can greatly contribute to extremely sustainable high performance facades. But before we talk about that, I want to talk about some of the challenges that our industry is facing and how these challenges present opportunities for us to not only design differently, but also evaluate materials differently. One of the biggest challenges we're facing is the rising heat index. As you look across Europe and even across the world, it's not just major cities like Manchester and London that are facing the urban heat or rising urban heat indexes and the heat island effect, but it's really every center where humans are living. When you couple that with the annual CO2 emissions, it paints a really bleak picture. 42% of all emissions come from the built environment, of which 2/3 are from building operations. So I'm sure you can see the correlation between building operations and the urban heat island effect and trying to combat that. So how do we solve for that? Well, that's exactly what a team from Danish Arkitekten, Nippers Helbig, Transolar, and Tri-Pyramid Structures looked to solve during our annual Architectural Ceramics Assemblies workshop. They wanted to create a wall system that controlled and slowed the flow of water across the facade to increase the evaporative cooling potential through terracotta. Before they got into design that, they first wanted to look at actually how they would support the terracotta. And as you can see on the charts, the initial baselines had a fair amount of carbon. What they were able to develop was actually a 50% savings with their fixing system. Then in August, they came to Buffalo, New York, and actually assembled a prototype and put it through a testing regiment, which included simulating a rain event. During that rain event, the exterior wall cooled by 11 degrees Celsius, and it remained 11 degrees Celsius cooler for the next 2.5 hours compared to the surrounding surfaces. So they did all this while also developing an absolutely stunning facade, as you can see here. So this is a really great proof of concept. How do we take this to market? How do we grow this? How do we find other solutions for terracotta to play a part in a more active facade? Everyone here is a creative thinker, and I challenge you all to think about that. What role can terracotta play in your next problem? For those who don't know about terracotta, terracotta is known for its malleability and plasticity before firing. Boston Valley employs the 4 commercially viable flooring methods for producing terracotta. Those are hand pressing, slip casting, ram pressing, and extrusion. Between all those different flooring methods, we can produce almost anything imaginable as long as gravity's on our side. To that point, we actually purposely bent extruded terracotta panels before they were fired to produce the terracotta units for the Newman and Rathbone passageways located in London, designed by Make Architects. This project also featured some really large hand-pressed bullnose pieces found on either end of the tunnels. Those bullnoses were approximately 400 millimeters tall and approximately a meter long. Terracotta is also known for its aesthetics. So Boston Valley has 14 standard natural through-body colors with the ability to customize. And then when it comes to glazing, the world's really your oyster. We can produce anything from a dry matte finish up to a high gloss. It can be a single solid color. It can be multiple glazes layered together. And you can also get some really unique qualities out of ceramic glazes that you can't from any other material, like translucency, crazing, breaking across edges. Really, the possibilities are nearly endless. A great example of this is the Project 60 Curzon, again in London. This was designed by PLP Architects, and they worked with a glaze developer before bringing us on board. Her name is Christine Yetten, and she developed the initial finish for it that we actually had to reverse engineer to work with on our kilns. The glaze is comprised of 5 unique distinct glazes that were all layered on top of each other to not only create a really unique pattern, but also create a texture because of the different viscosities of those glazes and how they melted out in the kiln. Terracotta is also known for its durability. It's a 100+ year building material, and it does not fade or degrade in UV. It's mold and mildew resistant, and it also withstands the harshest freeze-thaw environments. A great example is the Battersea turbine halls A and B. We were fortunate enough to be part of the restoration campaign, so the turbine halls were constructed approximately 90 years ago, and we replaced approximately 17,000 units between the two turbine hulls. We developed 3 distinct glaze color matches for it and produced 32 unique extrusion dyes for this heritage campaign. Terracotta is also one of the lowest embodied carbon building materials out there. It's extremely sustainable. Our terracotta production is actually 0 waste, and we can incorporate up to 30% recycled content into our mix design. For those of you who follow the circular economy, if in 50 years you get bored of your terracotta facade, which I highly doubt, you can actually pull it off the wall, crush it up, reconstitute it, and put it back into new panels that we can put back on the wall. A really interesting sustainable project was built recently in Toronto called The Well. It's a 6-building complex designed by Harini Pontarini, Adamson Architects, and BDP. It got its name because there's actually a 2 million gallon cistern located underneath the development that is part of Enwave's deep lake water cooling system and recently developed heating system. So this offers a really low carbon means of HVAC for not only the well, but also the surrounding neighborhood. The building features a lot of really deep profiles, some of the deepest I've ever seen, and they got the inspiration for these from the surrounding historic terracotta context. They also chose a variegated, 3-color palette for the project to pay homage to the historic structures, but also be able to create a bridge between the old and new structures. Another forward-thinking project that was developed during our architectural ceramic assemblies event is the project with a multinational team from Arup, comprised of a London, Toronto, and Los Angeles team. They wanted to develop a new wall typology, but before they did, they again studied and created a baseline of the existing embodied carbon within a wall structure. Terracotta did win out here, but they knew that they could do even better than what it has. So they took advantage of the structural capacity of terracotta and foam glass for its insulative properties to maintain a typical wall cross-section while developing a new system. They put it through the tests, and it passed with flying colors. And as you can see, they saved an immense amount of carbon from those baseline cases. They did this all while picking some absolutely stunning finishes, and even more impressive is this system would work up to 6 stories unsupported, and after 6 stories, you would just need minor post-tensioning required for it. So I've talked a lot about different ACOP projects, and I just want to finish on a couple others I find really interesting that we've developed over the years. The first one is with Jenny Elsner. They do a lot of historic preservation and heritage work in the United States and over here in the UK. They want to look to replace historic cornices, which are typically under-engineered and supported, and replace it with contemporary rain screen methodology to create a lighter weight system that allowed for ease of modulation for installation. Woods Bagot looked to incorporate PV panels within an articulated ram press terracotta panel to increase the solar capture rate, and also in their words, they want to beautify the PV panel. As a standalone, they're not the prettiest. Henning Larson and Thorin Tomasetti teamed up to build a carbon positive facade. So they actually encouraged moss growth to grow on the bisque portions of the terracotta panels that actually capture carbon as the building continued to be out in the environment. So it created a carbon positive facade and offset all of our carbon emissions. Cook, Fox, and Barrow Happold developed a masonry wall system that provided habitat for birds, bees, and fauna. And this was a very dynamic system where it was just a different element of rotation to create the different pockets for each of those different programmatic elements. Finally, Eric Perry and FMDC developed a very large module for the fishmongers in London. I think you can see where the shape came from. This was again for a feature wall, a green wall. And they want to encourage lichen growth on the pieces to, again, capture the carbon emissions there. So part of the glazing strategy was actually to simulate the lichen growth and then also allow for some bisque for the lichen to continue to grow on as years went by. So as you can see, terracotta can be so much more, a facade can be so much more beyond aesthetics, Beyond visual appeal, a terracotta facade can transform functionality. It can redirect sunlight, disperse heat, capture rainwater, and create habitats for birds, bees, and plants. The potential is immense. Our industry just has to embrace it. Let's reimagine facades as a dynamic element of the built environment. Imagine terracotta facades that do more. What new innovations can we unlock? How can these advancements shape high-performance facades that actively support a sustainable future? The possibilities await.
Right. This is the second time you'll hear me speak, which is probably for the best. Right, we've now got our panel discussion. So Giovanni Gori from Maface Engineering is going to come to stage. I can't see him because the light's behind him. There you are. And I'll let him introduce the panel to you directly.
Good afternoon, everyone. Manchester is changing at an extraordinary pace. Over the last decade, over 87 buildings, over 15 stories have been built, with another 49 high-rise buildings in the pipeline. Today, we'll explore the role facades play in Manchester's next chapter, from identity and performance to procurement, risk, and regeneration. I'm Giovanni Gori from Maface Engineering, and I'm joined by Adam Thornton from 5+ Architects, Daniel Mossman-Clark from Ryder Architecture, Aaron De Ara from Staticus, and Damien Bork from FCDO. Adam.
Hello.
Let me start with you. Manchester growth has been remarkable, but with that growth has also come criticism that many developments are beginning to look increasingly similar. As the city grows taller and denser, are facades still shaping Manchester's identity? Or are we increasingly assembling buildings from a catalogue of proven solutions?
Well, what is the identity of a city? What do people think of when you think of Paris? You might think of the Eiffel Tower. When you think of London, you might think of the Gherkin. 20 years ago this year, we completed the Beetham Tower here. It opened in October 2006. And for a long time, there'll be an image on the screen later where you might have thought the identity was the Beetham Tower. Now, more and more facades are popping up, and how do they relate to the identity? How do we construct them? Manchester, the city of mills. You might have taken some local brick, local people, built things locally, and we've moved from a local supply chain to a global supply chain. And so how on earth are we meant to keep that localism? There's an example on the screen later of a building in Leeds where we've tried to say the Peak District, the geology, all the brick colors relate to the local area. But a lot of the time that doesn't happen because it's just simpler and easier to look at the global supply chain. So local materials, local people making local things, we've really drifted away from that.
Yeah, very interesting, thank you. And a question to all. Who really gets the final say when cost, program, and procurement pressures arrive? Who would like to take these questions?
I mean, we're living in a world now where facades are more and more built off-site as well. Not only unitized facades where we work, but also precast facades, UHPC, for example. So I think we are in that globalized world where, which you mentioned, and it's just about actually trying to retain the context of where we're working. You still see now the materiality of the facades is super important for the architectural intent of the building. We saw one a bit earlier on this morning, how they're building terracotta at, very high-rise scheme there. And it's obviously that's to bring in the contextual part of what the facade is. It plays out in a difficult way in sometimes because yes, you are hit with like the commercial reality of that, particularly using things like terracotta. It's a beautiful product. It's a lovely product, but obviously it comes at additional cost to just potentially using aluminium and glass, which we see quite widely used throughout Manchester. So I think the standardization part is where then you can start to try to reuse some of the same details, create some form of like kit of parts mentality with your design, where then you can be leaner with the design, but still save enough back in the budget where you actually still can implement terracotta or you can implement GRC instead of just aluminium cladding. But it's all, every project is its own challenge, and you just need to work through that with the design team, the construct team as well, and hopefully get there on the budgets.
And how much of this standardization that you're talking about do you think it's made by choice, and how much is made by the pressures of procurement costs? I
think we are in a commercial world, and definitely in the residential part of the industry, we're all very familiar with the economic situations. You know, I was at UK Reef not last week, and a week and a half ago, and there everyone's talking about commercial appraisals not stacking up. So therefore, we are really in that world, and if we want to see these residential buildings being built out, we need to have that in mind at the beginning. When we're designing the building. So there's no point designing a beautiful building if you're not going to be able to afford it. So standardization plays a part there in enabling that design really, and trying to not do things as fully bespoke towers, but using kit, again, DFMA principles, where you can then borrow design from another project, which actually makes our design, for example, our design would therefore reduce our design costs and make things a little bit more affordable.
You can start off with the best of intentions. We looked at Islington Wharf, New Islington, and it was next to a canal. That was sandstone. We thought, right, sandstone, that's the material to pick. We thought sandstone, great. To get it from Cumbria was £3 million. To get it from India, ship it to America, and then put it on the building as a unitized system was £2 million. And so even though you start local, you end up with a global supply chain that says we can do it cheaper by not going local. So yeah, it can get really lost.
Yeah. And Daniel, we're talking about identity, standardization, global supply, and the city really evolving very fast. How do you maintain a sense of place and belonging while the city grows at this pace?
Yeah, of course, it's a great question, especially considering the landscape of Manchester, where we are today. I think over the past decade, we've seen a rapid development across the city centre. We've seen new neighbourhoods being formed, like Great Jackson Street, or when you look at the perimeter ring of the city centre, swathes of tall buildings, which just simply weren't there in the context of Manchester and what we know it in the urban fabric. There's one thing of, modern design and designing and delivering efficiency in commercial buildings, which all stack up. That question on place, I think, resonates with how we connect these buildings to the ground and to the communities in which they serve. So looking at that public realm and the place and that kind of third space model, making sure that these new neighbourhoods and districts that we're creating as the city starts to grow really start to connect back to that cultural piece. There's something that we worked with Lang O'Rourke and the council on the Aviva Studios, fairly recently handed over in Castlefield in Manchester. Now that's arguably a new neighbourhood. That building is surrounded by tall residential buildings. Through the planning permission, there was very onerous requirements put on that building as a theatre, as a cultural hub, which meant that the neighbourhoods around there, the neighbour over the road could sleep with their window open. Meanwhile, there's a rock concert going on in Aviva Studios. So technically, in how we specify facades and how we procure these buildings, we have so much more, there's a much larger ask when we're doing this with density in cities. Mm-hmm. But that mixed use and that connection to place and the ground, as I was saying, is vital to making sure that these places are successful.
Yeah, and let me bring Damien in on that. And from a public sector and long-term owner perspective, what should Manchester be most careful not to lose as it continues to evolve?
Yeah, again, I think that's a good question. I've been working in and around Manchester since around the year 2007-ish, and the likes of Howard Bernstein and the concept of original modern is something which sort of pervades I suppose, the way they've approached Manchester growth over the last sort of 20, 30 years. Now, original modern was originally created to highlight sort of philosophical and ethereal design concept, which you can see all around Greater Manchester, or Manchester in particular. But going back to the original question that you asked, we are sort of challenged, I think, now as to whether or not we are still seeing that play out in some of the buildings that we're getting developed and getting approved in the centre of Manchester, or are we moving more towards more replicable structures? Like Castlefield, you've got quite a lot of replicated high-rise buildings with the same facade structure. Now, is that true to the original modern theme? I suspect planners would argue it is, but I think there's a challenge to that these days. And I think that's one of the key things that I would say Manchester doesn't want to lose. It's that sort of fairly ambitious design attitude, really. But the challenges of commerciality are definitely going to run up against that.
And thank you for that. And circling back to the concept of identity and global systems being applied at a local scale for Manchester, I'd like to ask, is it a brick slip, unitized building, a brick facades?
Where do you start with that one? Bricks were meant to be in someone's hand to lay repetitively all day without a repetitive strain injury. That's why they're that size, they work that way. And then if we're doing a tall high-rise building, you would never have done it in brick historically. And yet, certainly in London, we put up buildings all the time which are yellow brick, multi-story high. And is it authentic to how you would have done it? No. So we then make it look that way. So we've picked up an aesthetic because we can, which doesn't then have that aesthetic. So yeah, I'm not a massive fan of using materials in an inauthentic way. If you're doing a 50-story tower, it probably needs a 50-story tower cladding product on it rather than something that had its time of handmade.
I'll maybe just jump in on there, and it's actually it's my pet peeve because from a subcontractor's point of view, you're often brought in at, I would like to think at stage 3 or maybe even just before, even stage 2, we'd like to be there, but quite often or not, you're there at stage 3, maybe going for a PCSA tender or even coming in at stage 4 under a normal tender. And by that point, so much of the design is baked in, so much planning risk is there if you are going to deviate away. And I think that's really has become over the years my pet peeve of having towers built in ways that just don't suit the construction of them, like the buildability approach. Particularly brick slips on GRC. It's, we've commercially benefited from it. We've done projects with that, but is it the right solution for the future? For sure not. Especially when we're up against contractual targets on embodied carbon, trying to make cost pressures work. It doesn't tick any of those boxes. The only one it really ticks is the context box in terms of, have we got a brick warehouse next door? Yes. Do we want to build a tower? Yes. Okay, let's put bricks in the tower. For me, that's maybe I'm being a bit harsh.
I think they have their place in the low level. Every tower has a base.
Yeah.
So then there is appropriate things, and probably Dan, you can probably pick up on that kind of.
Yeah, absolutely. I think there's a thing about honesty, right, in architecture, and that, as you say, you don't want to create a system which is false in a way. It shouldn't be used in that manner, and therefore we shouldn't use it altogether. But again, back to that question on place and that low-level connection to the public, I think that's when you start to read the landscape, and that's where the success is driven. That might be reuse, that might be looking at existing fabric within the city or within the site that we're working, so that we bring forward and we reuse buildings that are on that site, as well as build a big shiny new tower as well, so that we still have that authenticity of place.
Yeah, and going back, Aaron, to what you said about the commercial viability pressure, the procurement process, and so on. And going back to the local context of Manchester, what does a good facade performance mean for Manchester from your delivery perspective?
What a question.
Keep the rain out.
Yeah, I mean, ultimately, the facade is to keep the rain out and to keep, the people inside dry and warm and whatever, if you take it back to its real foundation principle. But obviously, facades have come on leaps and bounds, and they're now expected to do so much more than just do the fundamental principles. And I think every project is actually totally unique. We've heard of a number of projects today, and each of them have their own constraints, whether that be a site constraint, next to the railway, and as a result, they've got extremely high acoustic performances. But what we ask, or whether it's driven through thermal performances to achieve Part L, and because you want to have a particular window wall ratio or something like that. I think particularly what we're seeing today is actually structural performance doesn't really drive design. Whereas perhaps previously you might have been more led towards structural design. Nowadays the constraints are more towards the sizing of systems generally, panelization, etc. of unitized facades and precast. It's a lot more to do with how we're constructing things. So I think and a lot of the time they conflict, these performances, daylight versus G values, a sort of an obvious example, but there's a lot of conflicts in there, and that's why we just heard from the guys at BB7 as well about how design is iterative, and it needs to go through that process naturally just to make sure that you get the right balance of the performances for the project. So probably can't really give you a straightforward answer to that question, but it's a very project-specific answer, I think, and you just need to go on that journey with the right design and consultants team, and obviously pick the right facade contractor as well that can definitely help you.
Of course. But circling back to what you said before about the global supply, however, those are local constraints. Are we using then global solution to try to achieve local objectives in terms of Manchester specific?
Yeah, I think interesting point. We had you had the conversation there about the local stone being used, and personally, I would be a massive advocate for that as well. I think it would be great to be able to use it. I think it just comes down to supply chain and actually digging something out of the ground in Cumbria, shipping it to our factory in Lithuania, then shipping it back to Manchester to install it on the site. Is that sustainable? Or could we use German limestone that's actually just up, in relative terms, just up the road to our factory, which we can then bring to site, and actually you're reducing the overall embodied carbon. And it's those questions which I think when you have the early engagement piece with all of the parties involved that are actually going to deliver, that you actually get best value out of it. And I think that's.
Yeah, and Damien, we're talking a lot of durability, sustainability, not perhaps enough about maintainability. So from a long-term owner perspective, are we thinking enough long-term when we are designing facades for Manchester?
Yeah, I mean, I suppose that's a good question from a public sector perspective, from a local authority perspective. Cost is a principal driver, and we've got to, I suppose, weigh up those buildings that we're going to be considering more iconic, cultural, or perhaps administrative centres that speak a little bit more to the community. That's where the purse strings are unleashed a bit in terms of attractive and more imaginative facades. But you've always, in my experience, at least within local government, within central government, you've always got the FM team peering down your neck, asking about the long-term maintenance strategies, access strategies. So there's definitely a balance, but certainly with local government, it's very heavily weighted towards cost and ensuring that the initial construction value is as low as possible. The public sector, unfortunately, isn't particularly good at thinking long term. it's often more focused on the original cost value. You've got some more, I suppose, long-term thoughtful thinkers out there, but overall, we're focusing on the initial cost.
Thank you for that. And Daniel, keeping still the conversation around performance and with the local context of Manchester, what's your experience in the balancing performance and embodied carbon and sustainability targets? And if you can make any example.
Of course, yeah. I think when we talk about carbon, embodied carbon in the building, I think the first thing we need to do is take a look at the life cycle of that and not the upfront embodied carbon in a building. I think we often race to find the products which are the lightest on carbon, but actually when you dig a bit deeper in terms of the maintenance and the replacement of that system, you could be ripping that out after 20 years, as opposed to a product which has a slightly higher carbon or a considerably higher carbon impact initially, but that will last you the building lifespan of 60 years. And then at that point, we can look at disassembly, recycle, and reuse. So certainly, I think that would be the first principle that we look to consider, is that whole life carbon assessment. And also using materials for their purpose, right? So looking at kind of thermal performance in the building systems that we plug into our architecture. It's making sure that where we can, it's a fabric first approach, and that we don't specify materials which cause thermal issues. We see in the high-rise buildings, a lot of apartments across Manchester and across the UK now with a slightly warmer climate. There are internal issues there, overheating. What can we do with a fabric-first approach to mitigate that and ensure that the building's performance from a systems perspective isn't overly used? Yeah.
Yeah, on this regard, Ramboll made a nice case study today about the life cycle and the replacement, as well on performances. One of the first presentation from Robert presented the 10 principle which would apply to Manchester. But considering all this discussion and the pressures from the procurement and the cost and so on, Aaron, do you think, are we then creating ourselves problems in terms of maintenance looking forward at the next 30 years?
Yes, probably yes. I think, but are we in a better place to resolve that problem? Also, probably yes. So I think if we go back towards like the rent, we often get now this refurb or new build optioneering right at the beginning of the project, and often we get asked, okay, can we renovate that facade, or do we need to rip it out completely and restart? And I think the question there, it just comes down to doing a survey on the facade, making sure what it is and actually what can you reuse, what you can't reuse. Sorry, I totally lost the track of your question actually, so I've just gone, but remind me again, sorry, Giovanni.
Yeah, we were talking about life cycle of material and the balancing between sustainability and embodied carbon, and also standardization and the pressures of procurement processes, and what role do we play, and do we give enough attention at maintenance
for life cycle and
the design stage? So, but I think you're covered.
Access and maintenance as well is something that the strategy of access and maintenance is really something that can have a really big impact on the facade design as well at the beginning. So really been understanding like the replacement strategies that are expected. Are you going to have a BMU on the building, or is it rope access only, or what? Those are the really critical things which we all know, and many in the room will already know that has a big impact on actually the system design and therefore the aesthetics of the building as well. So yeah, they're absolutely crucial things which you need to build into that design. Yeah. Can have a cost impact as well, significant at sometimes. So it really is important. And I think just to pick up, we're seeing more and more buildings now being asked for, rather than 50-year design life or 60 years design life, even now 100-year design life on buildings. So people are trying to, some clients are really pushing for that as well, which I think is the right way to go, to try and build things which are more robust and maintainable and replaceable, on all the towers we're building. So how will we in 30 years, when the glass is potentially no longer in warranty, how will we reglaze all of those projects with people in situ? That's not I haven't got an answer for that one, but yeah, it's a question I sometimes do ask myself, and then I put it into a little cupboard and forget about it.
And moving from design to delivery, and following what you said, and also considering the delivery side, how is the procurement process and the involvement of specialist subcontractor changed in the last decade?
In the last decade, well, I'm not sure I'm totally qualified to say in the last 10 years, but I think from what I've seen in my time is that we are moving towards, and not only because of the need to do so and the better design output at the end of it, of that early engagement, is also we've just heard about BSR and especially on HRBs, about those gateway processes, and they're really also from a statutory point of view pushing that early engagement. We're seeing many more PCSAs engaged as a result of the BSR, which personally we think is a great thing, but it also brings its own challenges with like longer fixity from our side, so it raises our risk profiles on projects. But actually, at the end of it, you get there's pros and cons. So, but I think certainly early engagement PCSAs are absolutely valuable. And when I ever come across a QS that says they're not, I always try to change their mind, because I think it's absolutely critical.
It comes back to building performance. We really scrutinize building performance now. And as an architect, if I've got an entire building made of glass through one supplier where I don't have to think about the junctions, then actually I can be more confident that the air test is going to work because there's one building. Now, don't get me wrong, if you start me on overheating regulations on tall glass residential buildings, then you'd go, well, that makes no sense, because actually we should be making windows smaller and smaller and smaller. We should be keeping the heat out as much as possible, because we're in a situation where buildings are warmer. And yet we have these glass towers, and as you look at them, actually a lot of the facade is solid. But if I had a solid cladding manufacturer doing my metal panels, and I had my glazing manufacturer, me, the architect, gets stuck with the junction between the two. Is it going to be airtight between this? Is it going to pass its water test at 50 stories in the air? Was I even trained on that? No. Does my PI get nervous? Possibly. And so handing over the whole envelope to one contractor makes it a lot easier. It makes it more likely to perform. It makes the cleaning strategy easier, because as you say, if you've got one BMU cleaning one product, directly you've got a solid and a glass and a louver sticking out, and you're trying to clean it from above all those different materials. So I can absolutely see how we've ended up with buildings that are one supplier, one cladding material, because that's the technical world we live in, where performance is becoming really the driver.
And do you think that the current delivery models still allow room for innovation?
Absolutely. It depends. You can let it get out of control really quickly, because the only way we can do this is like this, says Aaron to my left, and I go, are you sure? And we have a bit of a fight on, actually, I want a non-horizontal transom on your unitized system that we did on the M Hotel down at Old Street. It's like, oh, we can't do that. So you have that. But cost comes back to it as well. We did Chancery Place on the back of King Street, and we had and wanted 4 glazed corners. And again, there's a nighttime image coming later on the screen. And the QS was like, no, you can't afford 4 glazed corners that were all curved. And it's like, well, that was at the time Structown, sorry. And they were like, well, we've got to make 4 different molds for the 4 different curves, for the 4 different corners. Can't afford that. Like, okay. So if we use the same curve, the same diameter on each of the 4 corners, can we afford it? And the answer was yes. And so when you work with the supply chain to ask the questions of, well, this is what I want, how do I get it? Then you can be. And so the earlier you get the supply chain involved, the more you can have those arguments, debates, whatever you want to call them, to try and get the product that you want.
I'd just say you've got more time for iterative design, and that simply ends up in a better product. And at the end of the day as well, the subcontractor is generally the one in the contract who's going to hold that risk on design liability of the facade. Therefore, why not involve that person earlier in the process so that actually you can have those conversations over a 2-year period rather than over a 1-year period, or even less if it's traditionally built, So I think it's absolutely value add. Yes, it means clients investing money up front a little bit more to get that design and to get that level of engagement. But certainly we're seeing the residential market through BSR that's something that is feasible, is possible. In the commercial world, it's happening in prime office. I think like prime office developments, it's definitely happening. But in the wide, the whole market, it's not quite yet fully adopted, I'd say, but it is. I see the benefits.
And let me bring Damien and the public sector perspective. And in the public sector, how do you balance the quality ambitions with the delivery constraints that we have discussed?
Yeah, I mean, I'm speaking a little bit from my current experience working overseas. We've got some really significant issues from a supply chain perspective, working in places like Delhi or Islamabad, or even in places in West Africa, because we're talking generally about embassies, and these buildings are often designed to be high-profile, attractive buildings that want to attract trade discussions or dignitaries from overseas. The facade is a really important element of that. We tend to find that we've got to look local in terms of other solutions that have been used in that city, in that environment. But it's not always that we can achieve what we're looking for. So in Delhi, we were looking at locally quarried porphyry or limestone, Jali type structures that were quite reminiscent of local culture and local significance. We've got this ambition around that quality, but often that local supply chain can't really deliver it. So sometimes we find ourselves going back to the UK or going back to more developed markets to get what is available locally. But from a local sort of Manchester perspective, I think you're constantly balancing. I think coming back to it again, but you're constantly balancing cost, and also from a tying into procurement, we tend to do anything more spectacular on a more sort of 2-stage approach, design and build, which again loses that control from the client.
And Daniel, have these pressures, in your opinion, improved the quality of projects, or have simply made the industry more cautious?
I think the short answer is both.
Fair enough.
So I think, whether it's a complex procurement route, gateways, building safety, building regulations, it's all changed and it's all fairly new to the industry, and we're still getting our head around all of that. That takes time, that takes frustration, and that takes a lot of kind of collaboration to get through that process. and we are learning lessons as an industry, and that is being streamlined. The benefit there is that that checking process is evident, and we can't escape that now. So in terms of when we look at building safety and quality, that's assured from today. So that's a huge benefit which we couldn't quite control before. Whether that was a contractor kind of serving a very severe VE on a project through a D&B contract, there's things there where once you peel back the facades, which we saw in an earlier presentation today, there are critical kind of safety issues which aren't evident in the building structure. So that's a huge benefit. We no longer, hopefully, will have that. The issue is that it takes a lot of time to go through these gateways as a team, and I think as a design teams and contractors, we rely on tested systems now as a route through. We rely on that dependable system which has the approvals in place and are ready to go. That limits innovation, that limits kind of creativity through the design process. I think a lot of design teams would be hesitant to instruct a change, whether that was for sustainability or design in terms of innovation, if there's something which is tried and tested. So I think looking ahead, the systems in place are brilliant. We need to learn as an industry to streamline that so that innovation can be accommodated as part of that process.
Very interesting. Last question on procurement and delivery, and who would like to answer that? So, considering all we have discussed, who makes then, and considering the context of Manchester, who makes the final decision on facades? Is it architect? Is it facade consultant, client, contractor? Who wants to answer?
It's not us.
It's not us either.
Fair enough. Well played.
Otherwise, they would all carry on looking exactly the same as well. So
Yeah, I wonder anything.
There's
built.
just one answer.
Obviously, the architect. But the architect, when we take on the role of lead designer, I think you stand more of a chance. I think the whole procurement is sometimes the architect is actually just the annoying thing in the corner, and the large D&B contractor is like, what do you want now? But generally, the planners want to have a say. The local public at consultation should have a say. The building regulations, how big a window, has a say. The height of the buildings, the way it goes together, the QS has a say. So there
Everyone wants to say, and no one is taking the responsibility.
Exactly. Well,
we'll take the responsibility.
Actually, you're usually well placed to take the final responsibility. But that's a good point. Conscious of time, we have to move into the retrofit topic, which is very interesting, because Manchester is, of course, not only the buildings that we are going to build, but also the one that we decide and we choose to retain. And Damien, given your experience, as you were saying before, on local authority development, national and international level of regeneration projects, what actually regeneration success looks like? Is it about carbon? Is it about historic and heritage preservation? Is it about civic value? Is it everything?
It is a good question, and I've worked on regeneration schemes in eastern part of Manchester, in Blackpool, in London as well. It fundamentally comes down to the resulting economic performance of that place. I mean, if you drew a graph which related gross land values to people's perception as to whether regeneration has worked, you'd probably get a very straight correlation. Clearly, it's not always the case, but anything which is attracting people to come, to work, to play, to live, to an area which has seen economic decline. Design is a key factor in doing that. Imagination, and selling the vision, utilising the assets like heritage, all drive that, if it's done well, the increased land values, which in turn bring higher value jobs, higher value premises, and ultimately a great desire to be in those spaces, which is what regeneration is for me.
Yeah. So you refer often to commercial viability, of course, and I'd like to bring Daniel in. And at what point then does retrofit stop becoming commercially viable and rational compared to demolition and rebuild?
I think it's a site-specific question, that one. There's lots of factors what kind of come into play in terms of viability and heritage retention. As an example, we worked on Pilgrim's Quarter in Newcastle with Arup Façades in the audience here. And we were able to retain the Grade 2 listed facade of a Carlisle house, it's called, in Newcastle, a huge building. We retained the full Portland stone facade and the dome of that. Very tricky in what we had to apply to that in terms of security measures, thermal, acoustic, and all the rest of that. But the building itself wasn't suitable for reuse. We converted that scheme into Grade A office. The floor-to-floor heights wouldn't serve modern-day building services systems and the ceiling heights that we needed for that. The column grid was irregular and tight. The core placement across the building didn't serve open plan office. So for many factors, we went through that optioneering with the client and with the full design team, and it just did not stack up. What did stack up was ripping the internal configuration out of that building and inserting new structure, new facades around that to create that. Now, in terms of viability for that project, we had kind of quantum on our side. We had over 460,000 square foot of net lettable space, which made that viability kind of argument very easy. It stacked up and that was fine. I think when you move to scale and you try to retain heritage, and again, depending on the sector and what you'll get out of that, it's a very different question.
Yeah, that makes sense. So you're talking about commercial viability, technical challenges, and also risk of not knowing what you're going to find. And on this topic, Aaron, as then you're going to take the responsibility, as we decided. How much risks are clients willing to take on retrofit projects?
The answer to that question, it kind of all depends on what is the retrofit. Is it just a light touch, changing some, to bring up a facade that's 10 years old up to sort of a slightly better aesthetic value? Or are you going into like a deep retrofit where you're actually taking the facade off, retaining structure and rebuilding new in a way?
Probably wrap up with a really local example, the Corn Exchange, Manchester. It was an inward-facing building. The floor was a metre above pavement. Didn't want the public in that building, but we had to go and lower the floors all the way around the outside to make it an outward-facing. So retrofit, you can reuse buildings. Is it heavy? Is it light? Go and see if it works now. But yeah, it took an awful lot of effort to bring that into use.
Thank you everyone. I think time is up. We have discussed about identity, performance, procurement, retrofit, and I think the common threads is that the facades are not only, of course, simple building envelopes, but are a key part of how cities evolve. Thank you all, and please join me in thanking all the panelists. Thank you.
Right, thank you all. All that really remains is we say thank you to all the speakers, to the sponsors, to the contributors, to Zak for organising the day. And please, thank you. Go network briefly with everyone else who's outside, talk to each other, and we'll see you next time, hopefully. Thank you very much.